Alright. Sorry guys, we have to redo the information for the military. For the Air Force. But I think it went well. I think we're okay. Let's get started today. Let's do 4 sessions. I'm thinking we do them first, to be honest. Like 4 first today. And then, if anything, we can rewatch the videos twice. Like we'll play at 1.5 speed, rewatch the videos twice. If we go through them, then afterwards we'll do Anki, and then afterwards we'll add it. But yeah, it's just because I did a little bit. I mean, I need to move. You know, we got to get moving. We have to get moving. Feeling a little bit slow for some reason. I'm so slow. Why is my wallet here? Oh, we'll also work out today too. I think it's important we work out. And I kind of like the setup where we put the desk up. So maybe when I'm feeling tired, I'll just stand up. I think that helps a lot. Helps a lot. Let's go ahead and get yeah. And there's another piece of info I got today. Another piece of info I got today for this weekend to go to the base and stuff like that, and what I need to do. No worries, we'll get it all done. Everything will get done. It has to. Let's go ahead and get some oatmeal. I like that we start with some oatmeal. Okay. So zoom in here now. Get out the old flash card. We might need two. We'll see. All right, guys. Another day. Let's put in. Well, I don't know. Let's put in at least 8 hours, I guess. Let's get it. Nothing to it but to do it. So we gotta get it. I don't really like how this is separated. Why is it separated, guys? I don't like that it's separated. Oh, we did overview them yesterday. Ugh. Let's do cell interactions. Which cell junctions. Cell junction image receptors. Ligand gated and ion channels. G protein, couple receptors, GPCRs. Enzyme linked receptors. Okay. Biosignaling questions. Sure. And then what's the next one? Transport across the membrane. Passive transport and active transports. How the thing move across the cell. Passive transports. Facilitate diffusion. Diffusion and osmosis. Exocytosis. Phagocytosis. Membrane potentials. And permeability and membrane potentials. Permeability. That's 2, and then we're going to do 2 more. Cell theory. Maybe it's this one. Eukaryotic cells? No, cell theory is different, huh? I don't know where cell theory is at. That's not, I don't know, it's not here. The one that has cell theory is prokaryote/bacteria, so maybe that's the one they're talking about. But that has its own section here, no? Prokaryote/bacteria. So it's not this one. I think it's a whole separate one. Let's see if we can find it.
Modern folk, we tend to take for granted.
Maybe this, I don't know if this is actually part of it or not. What else do we find on cell theory? Biological theory? History and development of cell theory. There we go. Oh, that's part of this one. Go back. I don't really know where this one's at. I'm just gonna go with like maybe just do, have this be a little bit. Did I do these already? I don't know when, but maybe we can just do this as a little bit of a, I don't know when I did this. I could do like some of this as a little bit of a cell theory, maybe. Kind of, we can do a little bit of these. Doesn't seem like it's that bad anyways. So we'll include this one as part of the cell theory. Well, all of these really. And sure. And then let's go back. Well, there'll be a lot in cell theory that I'll have to write. I'm gonna need a little bit more cards on that one, I guess. I don't know what cell theory is describing. Let's see. And then we have 1, 2, 3, and then 4 eukaryotic cells. Maybe it means, well, I don't think it means this one. Right? Who knows? It's probably in here somewhere though. No? It's already part of Unit 8, so I don't think so. It ends on cellular. Oh, so it ends on embryology. I think it's this one. My else is on embryology. There's 10 lessons here. How many lessons? 11. So I think cell theory is the one that's not really there. Oh well. I don't know. Whatever. Okay, so anyways, the next one's gonna be cell theory, which will. And the last one we'll do today is eukaryotic cells, which is lesson 4. Cellular organelles and structures. Characteristics of eukaryotic cells. The nucleus. Mitochondria. I feel great today. Oh my goodness. Endoplasmic reticulum. Golgi apparatus. Lysosomes and peroxisomes. Epithelial and connective tissue. And then after that, we'll do I guess actually we should probably review. Actually, I think after that, let's do add cards to the Yankee decks, or the Yankee deck. Then we'll go ahead and read the high yield guide on whatever we can find. And then we'll go ahead and review the Yankee cards last. That way I add the cards, and I review based on the added cards plus just a normal review that we have. And then I think that might be it for today. Cell theory is going to take us quite a lot. I don't even know. Maybe I should just grab this and we'll just read this. And we'll read it for cell theory. I need to do that. Maybe I can do that tonight or something. I'll just leave it there so I can do this other stuff. This is some side stuff that I have to do. But I'll do that later. And we'll grab that. We'll put that there and we'll read it when we get to cell theory. And then we'll go ahead and do the videos. Okay, we have our to-do list. I write this because it makes it a little bit easier for me to just kind of look up the stuff that we just went over and add it to the deck. Hey, thanks, JJ. I appreciate you. Thank you so much. I mean, you don't know. You guys' kind words keep me going, Help to keep me going. I appreciate it. Appreciate all the love and support. Thank you. Really. All right, I think we might get started pretty soon. Well, we're gonna get started here. Not here, but we'll get started right now. I wanted to give this another redo for today and see if I can bring this up. I was really tired yesterday, so maybe I can just start with redoing this first. Let's take off the jacket. And then unless I'm hungry, I'll go out, but otherwise, we'll just take the breaks. We'll just take the breaks here and see if we can do a little bit more exercise sessions today. We got to get a little bit ahead because I have to go to the Air Force Base this weekend and do whatever they want me to do. That's going to take some time. I'll stream when I come back. Can't stream at the base. It's not allowed. It's not allowed. That would be right. Yeah. So, cholesterol at low temperatures will help to decrease the distance between the phospholipids, fatty acid tails, and that's what's going to increase the fluidity. So we got two here that say increase the fluidity to low temperatures, A and C. And then at high temperatures, though, it's actually going to decrease the fluidity. So we got C. Compared to a typical animal cell, the cell membrane on the paw of the polar bear, the black part, the polar bear paw, will most likely have an increased concentration of which macromolecule. Whoa! There goes my speaker. Jesus. Also, why didn't I didn't even set it up properly. Actually, it's a good thing the speaker fell out because I needed to realize that the timer hadn't started. You can tell I'm out of it. I'm freaking out of it, man. We're supposed to set this one up for 60. Right? What the heck are you doing, man? There we go. Alright, we set it up for 60. My eyeball. Oh, dude, I got a piece of my hair on the oatmeal. So what? So what is anybody gonna do about it? That's Mike Tyson. He said, so what? Mike Tyson said, so what? Let's put it somewhere. Pause it. Let's put it over here. All right. I'm awake. Wake up. So I think it said all living systems. Was it not living systems? Like, eukaryotic organisms need more fluidity in the cell. That was it. So it's just a basic plain, animal cells require more fluid in the cells, right? Or require the cells to be fluid. But yeah, because at low temperatures, crystallization is gonna be easy to break the cell, which isn't what we want. So just plain old, that's it. So I think if it's unsaturated, then we're lowering the fluidity because we're increasing the distance of the phospholipids. Too far apart, man. So there's just anything gets in. Anything's getting in. So we're not going to do that one. And then that's going to be saturated. We want saturated with hydrogen atoms neatly stacked together. Very tight, less fluid. Oh no, that's very tight, less fluidity. No, that's very tight. Wait, that's very tight, less fluidity. I think it messed me up. Maybe about that. But the polar bear lives in a colder place. So they're already going to be saturated. Which they have cholesterol too. I think saturated, right? Because they're gonna be more tightly packed. They're getting more tightly packed. I'm sure polar bears get cholesterol from animals they eat. So that's gonna help increase the fluidity, right? You'd want them to be more tightly packed. So that not so many of whatever molecules gets in easy. Right, like water, for example. Water we're getting slowly if it's saturated. And we don't want that much water in the cells. Otherwise it's gonna swell up. I don't think we want that for the polar bear. We don't want the paw to swell up. So we need it to be saturated. To be less saturated to be a little bit less fluid. I think it's saturated. Oh no, it wasn't saturated. Oh, it was unsaturated. Oh man, my logic is not good, I guess. But yeah, it must be able to tolerate low temperatures. For the cell to function, it must increase membrane fluidity. Oh, okay. I still got this one wrong. Okay. They got it wrong yesterday too. Membrane fluidity. Oh, okay. For it to function in low temperature, we must increase membrane fluidity. For it to function, we must increase the membrane fluidity. Gotcha. Because if it's too if it's not that fluid, it's gonna break in cold temperatures, right? We need it to be more fluid. Okay. All right. Okay. Most quickly, glucose too big, benzene too big, urea. I'm not sure. Ethylene. I think it's alcohol, but I think ethylene is small, right? Oh, and it's not polar. What does urea look like? Oh, by the way, you guys aren't even seeing what I'm doing. Okay. All right, JJ. Good luck, buddy. Maybe I'll probably touch upon some of the stuff you'll be learning eventually. I'm sure it'll cross. What does urea structure look like? Oh, okay. Okay. That's what you got going on, huh? I think ethylene is just a little bit smaller, and it's also very non-polar. Gotcha. C2H4. Okay, great. Perfection. Let's get out of here. So with stability of cell of a thermophilic bacterium. So for eukaryotic cells, at low temperatures, we want more fluidity. I guess that's just law, basically. So, but for thermophilic, heat-loving, if it's heat-loving, we would want well, I don't know. Do bacteria have cholesterol? That's a good question. Do bacteria cells contain cholesterol? I don't think so. I can't even spell. Okay, so they don't have cholesterol. Okay, well, yeah, I mean, well, sure. So if they don't have cholesterol, at cold temperatures we want more fluidity, so we want unsaturated. At more warmer temperatures, we'd want saturated, because it's the process of them increasing in this sense that will increase the fluidity at that point, which is what we need for survivability of the cell. So we're going to look at the longer chained fatty acid. Damn. Is that what it is? But decrease the fluidity of the cell. Saturate. Decrease the fluidity. Decrease the fluidity of the cell. Is that what I said? Decrease the fluidity of the cell. Or no, maybe not. Maybe not really. Let's try to figure this out. You made a mistake in the notes. I thought at high temp it's going to increase in fluidity. That's really what the guy talked about. I have it in the notes. Distance, further distance, increase in temp, increase in fluidity. But I also have, if it's saturated, it lowers the fluidity. Oh, but at hot temps we would decrease the fluidity to keep the membrane from melting apart. Oh, okay. The membrane from melting apart. Gotcha. Mm. At times you need to decrease the fluidity to keep the membrane from melting apart. What does that mean exactly? At times we need to decrease the fluidity. Oh, okay. Sure. Okay. I think I was thinking about it a little bit wrong. I think now I kind of understand it. Gotcha. I think you see glucose is a huge molecule. This one does not require ATP. Facilitate diffusion. I think it's C, right? Yeah. The rate. Yeah, this just depends on the amount of ions, right? Or the concentration gradient. Well, ions. And this one is going to be, it's determined by the number of transfer proteins. If there aren't that many, then the rate of physical diffusion is going to go down. Okay. Is the path that sends it across the membrane without the aid of integral membrane proteins? But it does use a channel protein. Does it mean like it doesn't really? The channel protein just allows it to flow through, but doesn't really help it. Without external, you cannot transfer ligands. Oh, gotcha. I think it's in the process of if it needs ATP or not. And the channel proteins don't need ATP. So I think that's what it's talking about here. It says without the aid of an integral membrane protein. one thing? No. Let me see. Okay. And there's no. I think it was. Oh, to store electrical tension. Well, whatever. A little better it is. Alright, let's just continue. Anyways, second part was cell-to-cell interactions. An article. Right. I can't see. Oh wow, that's really cool.
Mm. Wow. Wow. Incorporate proteins into the cell membrane. Get out of here. A bit too much, I think. It's like a bit too zoomed in for my taste. But I need to be able to see it. Something like here, I guess. Gotcha. Pino, like Pinocchio, receptor mediated endocytosis. Hmm. Hmm. Oh, it was another one. Okay. Absorption of 5%. Oh. Hmm. What is this? Wouldn't this be step 2? And this be step... Well, I guess this be kind of part of step 2. They need to redo this. Absorption of phagosome. Absorption of phagosome. Absorption of the phagosome. Absorption. Okay. Particles, imagination, invagination, membrane fusion, membrane fusion, vesicle formation, vesicle disintegration. Okay. Okay. Oh. Sure. Oh, okay, this is the one I was looking at. Receptor-mediated endocytosis. Um, is that right? Okay. Gap junctions. Tight junctions. And decisomes. Desmosomes. Desmosomes. Sure. So, but is that it? I mean, is that it? What the heck? Sure. Okay. So, I mean, tight junctions. I mean, there's. Okay. Sure. Okay. What is the tube made out of? And if tight junctions are, there are connections that form each other's core shell. They help connect the same membrane, form a tight junction, a tight seal. Imagine if watertight seal. Okay, imagine the intestines or kidneys. Fluids like a urine be circulating throughout your body. Mm, oh, okay, yeah. I guess so. Sure. Some memories are connected by thread-like substances across the space in between the cells. Oh, hmm. Okay. Let me see what it said. That's cool. Ectothermal dysplasia. The heck is a rivet point? Hmm. Hmm. Oh. Teeth, hair, nails, and so CX43 and CX55.6. Oh, brain tissue. Oh my goodness. No. No. Oh. Okay. Skin blistering. What is skin blistering? I've had those before. I had a big one last time. I used to get them all the time as a kid, actually. Now, not so much. I haven't gone in quite a while. Mistakes in our genes that produce this cause skin blistering. Cause skin blistering? Oh, there's no structural support. That's a good question. I don't know. I'm the answer. That's it, huh? Sure. If you were building a building, if you were building a building, what kind of connection might you want to put between the rooms? Between the rooms? Maybe a hallway, some doors, right? Sure. You want me to walk in the room. You put a door. Spot weld. Spot weld. Okay. Maybe just take this one out, I guess. Plasmodesmata. Plasmodesmata. Singular plasmoda. Plasmodesma. Plasmodesma. Hole punched in some wall. It's not a plasma exchanges between the two cells. Vacuum. Sure. I need the band, dude. I need to focus. I know with the plasma membrane. Size exclusion limit? Process is poorly understood. Interesting. Connexon. 6 membrane proteins. Membrane. Well, it's got to be transmembrane protein, right? Because it has to go. It has to go through the entire cell membrane. What is a membrane? Alright, what the heck is? I need some more energy. Alright, good luck, JJ. You got this, buddy. We should stand up, move around. All right, let's get back. Oh. Connexins form connexon. Invertebrates. It's insects, right? You know insects? Oh, a lot more than just insects. Okay, sure. Okay. Okay. Connexon closed. Open. Okay, okay. Load. There we go. That's what I want to see. Cytoplasmic connection. Claudins. Claudins. Interesting. Dum, 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 dum. Groups of tight junction proteins. I mean, so they also go through the cell membrane and literally connect them both to each other. Literally connect them both to each other, forming a tight seal. Extracellular space. I thought we don't want anything going through here. Why do I see some gaps? What the heck? What the heck? Why are there still some gaps? Oh, and then also. Oh. Yeah. Not a pretty good image. If it wasn't so tiny. These are desmosomes for structural support. Can't hear it? No. Maybe some of these. Intermediate filaments of cell 1. What the heck? Intermediate filaments. Linker glycoproteins. Black. That's like a good image too. I can see. I can see clearly now the rain is gone. Clear and clear. If you're having trouble with allergies, take clear and clear. Microphone. Adherence attached to the plaque. Adherence attached to the plaque. Linker glycoproteins attached to the plaque. And then the filaments do what do they do? Adherence attached to the plaque. BBB, the blood-brain barrier, likely has many tight junctions. Okay. Sure. Alrighty then. Video time. Hopefully see the guy.
Cell junctions.
Oh, this is pretty good.
In this video, we're going to talk a little bit about cell junctions. Cell junctions are basically things.
Well, let's get my jacket. Kind of cold right now for some reason. You know. We should exercise after this. Do a little bit. A quick 15-minute of a break. 15-minute break, and just work out a little bit. Maybe work out again later tonight. Maybe see if we can try to work out 3 times, but if it's just 2, I'll be happy.
That connect cells to other cells, and they often occur in epithelial tissue. We're going to talk about 3 major types of cell junctions today. The first, tight junctions, the second, desmosomes, and the third, gap junctions. So starting off with tight junctions. Let's say we have 2 cells like this. So tight junctions basically connect the 2 cells together. And it's kind of like a glue that connects them together really tightly like that. I think of it like a watertight seal. It's a complete fluid barrier, which means that if there's water or ions or other molecules trying to get through between the 2 cells, they would not be able to. So it blocks out pretty much everything from both sides of the cell. So water and ions cannot go through that gap between the 2 cells. Sure. This tight junction, this watertight seal, tends to occur in things like the bladder, for example, or sometimes intestines and their kidney. They occur in places where water really cannot go to other places. For example, our bladder holds urine, which is waste. And it would be really bad for our body if our bladder was unable to be watertight to hold that urine just within the bladder. The next type that we're going to talk about are desmosomes.
I guess now I'm actually thinking about it. I think this is within the bladder cells, right? So it creates a tight seal around the cells of the bladder, inside the bladder, right? And it would be funny if yeah.
Now let's say we have, again, 2 cells like this.
We'd have urine.
What desmosomes do is, I'm exaggerating the gap between these a little bit, but they're kind of like connections that hold two cells together. And these connections actually attach inside the cytoskeleton. And again, this gap is exaggerated. Usually the cells are a little closer, but in desmosomes, if there is water or ions, they can actually flow between these cells. So ions like sodium or potassium or water or other small molecules can actually come through in this gap. I like to think about desmosomes kind of like spot welds. They kind of hold the two cells together, but it's not like a complete glued seal like the tight junctions. They're kind of spotted throughout the cell so that things can actually flow in between the cells. Desmosomes tend to occur in tissues that experience a lot of stress. They offer a little bit of space for stress relief. So these spot welds, these desmosomes can be found in our skin.
Hold on, guys. 1 second.
Oh, that's actually pretty early. Oh, that's it. Oh, I would have thought it was going to end a lot later. I did print out the schedule for this week. It's in 4 days. I want to be ready. Gotta be ready for this Saturday. Let's continue.
And in our intestines. Now you notice that our intestines actually has both desmosomes and tight junctions. These cell junctions can be scattered throughout even the same type of cell. So intestinal tissue can have both tight junctions and...
I really like this image. I don't know. It's like very clean. And I'm zooming in and zooming out. What the heck? Should I be zooming out to zoom in? Kind of, huh? Tight junction here, tight junction here. Oh no. Gap junction. So I think it's this gap junction, tight junction, desmosome. What is this? What is that? What kind of thing is that one? I don't know. What's the middle part? Adhesive belt. Oh, it's an adhesive belt. Oh, okay. I don't know. We're not there yet.
and desmosomes. The last one we're going to talk about are gap junctions. So let's say we have, again, our two cells like this, gap junctions, and again, I'm exaggerating the size of our gap junction, but they're kind of like a tunnel that actually exists between the cells. So they're like a tunnel. And what they do is they actually let water and ions and so on flow through this gap between the two cells. So they're kind of like a tunnel. These are often found in cells or tissue that spread action potential, or cells that use electrical coupling. For example, they can be found in cardiac muscle. This allows our cardiac muscle to actually spread action potential by using these ions. This allows our heart to continue beating. It can also be found in neurons. So in summary, we have three main types of cell junctions. The first are tight junctions. These are a watertight seal which prevents water or ions from flowing in between cells. We have desmosomes, which are spot welds. And these spot welds generally occur in areas of stress, and they also allow water, ions, and other small molecules to flow between cells. And the lastly are gap junctions. And gap junctions are tunnels that kind of connect two cells. And these tend to occur in cells that require propagation of electrical signal.
Sure. Thank you. Thank you kindly. Thank you, kind sir. I am sorry. Before we start this next episode, let's go ahead and log in real quick. Oh, seriously? Seriously? I just want to log in. Who's this? Hold on, guys. I need to check this message real quick. Nah, there's nothing there yet. But I wanted to see, because it's had to check up on my stuff. Looks like they're always listed though. So I don't think. Hold on a second, guy. For who? Oh. And I'm third for Deborah, and I'm 14th for Catherine. Oh, okay. That's actually pretty good. Hey, that's pretty good. All right, let me mute it real quick because I want to check what who emailed me.
Membrane receptors. Membrane receptors are really important because they are the things that actually allow our cells to communicate with the outside world. Without membrane receptors, our cells wouldn't be able to work together and they wouldn't be able to form the human body as we know it. And so a membrane receptor is essentially an integral protein that is embedded in the cell membrane that takes part in communication with the outside environment. And so for short, I'm just going to say it's an integral protein that communicates with the outside environment. And so the way membrane receptors work is that in our bodies, there are a bunch of these signaling molecules going around. We call these extracellular signaling molecules because they are outside our cells. So let's say this outside area is the extracellular portion. Let's say we have a pink signaling molecule. And for the sake of diagramming, I'm going to say it looks like a triangle. Now, in reality, of course, signaling molecules do not look like triangles. Signaling molecules can be a variety of things. They can be ions or molecules, essentially, that bind to another chemical entity. We also call these ligands. Molecules going around. We call these extracellular signaling molecules because they are outside our cells. So let's say this outside area is the extracellular portion. Let's say we have a pink signaling molecule. And for the sake of diagramming, I'm going to say it looks like a triangle. Now, in reality, of course, signaling molecules do not look like triangles. Signaling molecules can be a variety of things. They can be ions or molecules, essentially, that bind to another chemical entity. We also call these ligands. And a ligand can be something like a neurotransmitter, a hormone, cell recognition molecules. And what these can do is these can attach to our membrane receptors and trigger changes inside the cell. And I'm going to do the membrane receptors in a nice blue color. And remember, we say they're integral proteins, and integral proteins are proteins that go through the entire cell membrane. So let's say here we have our nice integral protein. And so what will happen essentially is this ligand will bind to our integral protein. And so this integral protein, which again appears in our cell membrane, will actually bind to that nice triangle-shaped ligand that we have, like this. And so now what we have is our ligand receptor complex. Just a fancy way of saying our ligand and our membrane receptor have bound. And once this happens, this can essentially tell the cell what to do. This can explain things like how hormones function, how our nerve impulses work, why our cells divide, cell death. It also explains why our cell allows certain things into the cell and other things not sometimes. In terms of a bigger real-world application, this is really critically important in designing pharmaceutical drugs. In fact, a very big percentage of pharmaceutical drugs actually target our membrane receptors. This is actually why some drugs can target specific cells, like some drugs might only target your liver, while other drugs might target your heart. And the reason why is because different cells might actually have different receptors, and these receptors might bind different things.
Gotcha.
This whole process of
okay. Wow.
binding and telling the cell what to do, we actually have a really special name for it, and that's called signal transduction. So this is a process that we call signal transduction. What happens during signal transduction is an extracellular signal molecule, so this is our ligand, binds to our membrane receptor, and these receptor proteins then cause an intracellular response. And so after binding, there will be what's called an intracellular response. And so this receptor will bind to the protein, and this will cause the protein to actually change conformation, which then activates intracellular signaling proteins, so proteins on the intracellular side of the cell. And this activates a cascade of protein signals that will alter the behavior of our cell. Sounds really complicated. Essentially, the way this works is we have an original signal, our ligand. This can be, again, a hormone, a neurotransmitter, something like that. And this original signal is passed along. It'll bind to our protein, and that protein will tell other proteins inside the cell about what's going on. And this signal is propagated throughout the cell, causing the cell to perform a specific function. Now, you'll notice that in the diagram, we actually drew a really specific shape for our ligand. We chose a triangle. Now, I chose a triangle because it's a little easier to draw, but this triangle actually fits right into the protein that I was drawing, which has like an empty triangle space. This is actually really important. Each specific receptor, so the thing that's missing a triangle, can only bind to a few types and often only one specific type of ligand. So it can only bind that specific triangle pinked ligand. Membrane receptors allow our body and cells to transfer information, and it can be very, very specific about it. This is important because when our body releases a hormone, it's kind of floating around in our entire bloodstream. How does our pancreas know that the hormone's intended for it? How would our heart cells not react to it? And this is why. The membrane receptors have a very specific preference for certain specific types of ligands. This is what we call our lock and key model. So if we imagine our ligand as the key and our receptor protein as a lock, our receptor protein as a lock needs a very specific type of key in order to open it. So just like how our keychain, we might have a key to our mailbox and a key to our front door, maybe a key to our desk. Each of these keys does something different and opens a different lock. And that's kind of how our cells work. Now, I just want to make a note that this is a slightly outdated model. And our updated model is actually what we call induced fit. And these two concepts are very similar, but instead of saying that the ligands and the membrane receptors have very, very specific shape, induced fit brings a little more flexibility. And it says the ligands and the membrane receptors can sometimes change conformations, kind of like how dough can be a little squishy so that they can fit each other. Now, overall, there are still a ton of new membrane receptors that are being discovered. As far as we know, we can group membrane receptors into three large groups. The first group we call ligand-gated ion channels. The second group we call G-protein coupled receptors. And lastly, our third group we call enzyme-linked receptors. Now, in summary, essentially we have really important membrane receptors in our cell membrane. And these are integral proteins that allow our cells to communicate with the outside environment. And the process in which these integral proteins work, these membrane receptors work, is that we have a ligand, which can be an ion or a molecule. It can bind to our integral protein, causing a process that we call signal transduction. And signal transduction essentially means that our original signal or ligand is propagated throughout the cell as different proteins are activated, causing our intracellular response. Ligands and membrane receptors have a very specific fit. Only specific ligands can bind with specific membrane receptors. We call this lock and key. A more updated name for it is induced fit, in which the ligands and membrane receptors are a little more flexible, kind of like dough. They'll actually slightly alter conformations when they fit together. And all of these membrane receptors that we know so far can be grouped into three major groups: ligand-gated ion channels, G-protein coupled receptors, and enzyme-linked receptors.
Very nice, very nice. Everyone here, they're already graduating medical school. Oh, he's going over them right now. Excuse me. Let's go to the bathroom. Let's go to the restroom. I need to pee real quick.
Oh, I've fallen. I've fallen and I can't get up. Call 911. Okay, let's go.
Have you ever wondered how our nervous system, like our neurons in our brain, can react so quickly? Well, the reason is because of ligand-gated ion channels. Ligand-gated ion channels are one type of major membrane receptors. The three categories are ligand-gated ion channels, G-protein coupled receptors, and lastly, enzyme-linked receptors. Today, we're going to focus on the ligand-gated ion channels, and these are also called ion channel linked receptors. So ligand-gated ion channels are transmembrane ion channels that open or close in response to the binding of a chemical messenger like a ligand. So like we mentioned, a very common place to find ligand-gated ion channels are in electrically excitable cells like neurons. And the reason why is because these ion channel linked receptors. So ligand-gated ion channels are transmembrane ion channels that open or close in response to the binding of a chemical messenger like a ligand. So like we mentioned, a very common place to find ligand-gated ion channels are in electrically excitable cells like neurons. And the reason why is because these ion channels, so like we mentioned, a very common place to find ligand-gated ion channels are in electrically excitable cells. Cells like neurons. And the reason why is because these ion channels react really quickly to the binding of ligands. And so they're very commonly found in cells that need to react very quickly to stimulus. When we talk about transmembrane ion channels, what we really mean is they are transmembrane or integral proteins that also have a channel, a hole through them in which things can move in and out. Transmembrane or integral proteins that also have a channel, a hole through them in which things can move in and out. So to start with, let's say we have an ion channel that looks something like this. Let's go ahead and color that in. And this particular channel, this channel at the moment is closed. And right now we have our intracellular environment here. This is where our cytosol and all of that stuff is. And this is our extracellular environment. And so as you can see, this ion channel has like a weird kink in it. And this is this place where a messenger, like a ligand or a neurotransmitter, can bind. So let's say we have a ligand that looks like this. This is our ligand. And this ligand can bind in there. And you'll notice that the shape of our ligand is complementary to the shape of our channel. And so it fits right in there. So only specific ligands can bind to specific channels. This is what we call our lock and key, or it reacts so quickly. Well, the reason is because of ligand-gated ion channels. Ligand-gated ion channels are one type of major membrane receptors. The three categories are ligand-gated ion channels, G-protein coupled receptors, and lastly, enzyme-linked receptors. Today, we're going to focus on the ligand-gated ion channels, and these are also called ion channel linked receptors. So ligand-gated ion channels are transmembrane ion channels that open or close in response to the binding of a chemical messenger like a ligand. So like we mentioned, a very common place to find ligand-gated ion channels are in electrically excitable cells like neurons. And the reason why is because these ion channels react really quickly to the binding of ligands. And so they're very commonly found in cells that need to react very quickly to stimulus. When we talk about transmembrane ion channels, what we really mean is they are transmembrane or integral proteins that also have a channel, a hole through them in which things can move in and out. So to start with, let's say we have an ion channel that looks something like this. Let's go ahead and color that in. In this particular channel, this channel at the moment is closed. And right now we have our intracellular environment here. This is where our cytosol and all of that stuff is. And this is our extracellular environment. And so as you can see, this ion channel has like a weird kink in it. And this is this place where a messenger, like a ligand or a neurotransmitter, can bind. So let's say we have a ligand that looks like this. This is our ligand. And this ligand can bind in there. And you'll notice that the shape of our ligand is complementary to the shape of our channel. And so it fits right in there. So only specific ligands can bind to specific channels. This is what we call our lock and key, or a more updated one is called induced fit. So once this ligand binds, what it'll actually do is it'll cause this closed channel to actually open up. So what we'll see is we'll actually see this channel open up kind of like that. So now this is our open channel. And so one really interesting thing about ligand-gated ion channels is if you look at where this ligand binds, the binding site of this ligand is not anywhere near the actual channel. And the reason why is because this is what we call allosteric binding. And so the ligand binds to what we call an allosteric site. This is a place that's away from the ion channel. But what happens is once the ligand binds, it can control the opening and closing of the ion channel by altering the protein conformation of the entire protein. So once it binds, a channel opens in a different place, and the ion permeability of the entire plasma membrane can quickly change. Remember, this is not just one thing happens by altering the protein binds to what we call an allosteric site. This is a place that's away from the ion channel. But what happens is once the ligand binds, it can control the opening and closing of the ion channel by altering the protein conformation of the entire protein. So once it binds, a channel opens in a different place, and the ion permeability of the entire plasma membrane can quickly change. Remember, this is not just one thing happening. When these ligands are binding, there are many of these channels scattered throughout these cell membranes. So all of these are opening and closing all at once. So once this channel opens, it'll let ions like potassium, sodium, chlorine, or calcium being the most common, move through the open channel. And so once these ions are moving in and out, this will cause a change in the electrical properties of a cell. In other words, you'll convert this extracellular ligand signal into an intracellular electrical signal. And so once these ions move in, or they can also move out, you'll have an intracellular electrical response, electrical signal happen inside the cell. Okay? So there are two things I'd like to note real quick. The first is that the allosteric binding site of a ligand, so this area that is complementary to the ligand, can be intracellular, it can be inside the cell, but that's considered pretty rare. Why might that be? Well, we'd have to think about the main purpose of membrane receptors, and we have to realize that they generally are meant to respond to extracellular signals, to things that are on the outside of the cell. And so generally speaking, ligand-gated ion channels will have the binding site on the extracellular side. The second thing to note is that it is possible for there to be multiple allosteric binding sites for ligands. So it's possible that there are multiple of these kinks, of these complementary shapes that let the ligands bind for each protein. Now, finally, I'd like to clear up two quick misconceptions. ligand-gated ion channels are easily confused with two types of ion channels. They are not the same as voltage-gated ion channels. Voltage-gated ion channels rely on the difference in membrane potential. And as we recall, ligand-gated ion channels actually respond to the binding of a ligand. The voltage-gated ones only depend on the difference in membrane potential. The second one they're easily confused with is what we call stretch-activated ion channels. Now, as the name implies, stretch-activated ion channels depend on what we call the deformation of the cell membrane, or the cell membrane stretching and being pushed and being stressed. So in summary, ligand-gated ion channels are one type of membrane receptors. They are transmembrane ion channels that open or close in response to the binding of a chemical signal like a ligand. So you'll notice that here our channel is closed, and once this ligand binds to an allosteric site, which is a site that's not on the channel itself, and it'll let ions such as potassium and sodium and so on move through the membrane. This will actually cause an intracellular electrical signal. So we have one outside ligand, and this will allow us to have an intracellular electrical signal. And this will actually tell the cell to do something. And ligand-gated ion channels are not to be confused with voltage-gated channels, which only rely on a difference in membrane potential, and they are not to be confused with stretch-activated ion channels, which are affected by deformation of the cell membrane. Which are affected by In this video, we're going to talk about G-protein coupled receptors, also known as GPCRs. G-protein coupled receptors are only found in eukaryotes, and they comprise of the largest known class of membrane receptors. In fact, humans have more than 1,000 known. In this video, we're going to talk about G-protein coupled GPCRs. G-protein coupled receptors are only found in eukaryotes, and they comprise of the largest known class of membrane receptors. In fact, humans have more than 1,000 known different types of GPCRs, and each one is specific to a particular function. They are a very unique membrane receptor, and they are the target of around 30 to 50% of all modern medicinal drugs. In fact, the ligands that bind range from things like light-sensitive compounds to odors, pheromones, hormones, and even neurotransmitters. 30 to 50% of all modern medicinal drugs. In fact, the ligands that bind range from things like light-sensitive compounds to odors, pheromones, hormones, and even neurotransmitters. GPCRs can regulate the immune system, growth, our sense of smell, taste, visual, behavioral, and our mood, including things like serotonin and dopamine. Even now, many G proteins and GPCRs still have unknown functions and is a topic heavily researched. In fact, in just 2012, a Nobel Prize in Chemistry was awarded for research on GPCRs. To start off, let's talk a little bit about the structure of GPCRs. It's impossible to really have a discussion about how GPCRs work without having an understanding of what they look like. The most important characteristic of GPCRs is that they have 7 transmembrane alpha helices. If we have this being our cell membrane, and we have this being the extracellular side, and this being the intracellular side, if we have a GPCR, a G protein coupled receptor, it'll span this membrane 7 times. So let's say it starts here, and we go 1, 2, 3, 4, 5, 6, 7. This is one of the most important characteristics of a GPCR. They have 7 transmembrane alpha helices. Since this is such a unique and interesting structural characteristic, we often also call GPCRs 7 transmembrane receptors. So just to quickly label, this is our GPCR here. As the name implies, GPCRs interact with G proteins. They're coupled with G proteins. Now, it's important to talk a little bit about the structure of G proteins also. G proteins, in general, are specialized proteins which have the ability to bind GTP and GDP. In other words, they are able to bind guanosine. If we have a GPCR, a G protein coupled receptor, it'll span this membrane 7 times. So let's say it starts here, and we go 1, 2, 3, 4, 5, 6, 7. This is one of the most important characteristics of a GPCR. They have 7 transmembrane alpha helices. Since this is such a unique and interesting structural characteristic, we often also call GPCRs 7 transmembrane receptors. So just to quickly label, this is our GPCR here. As the name implies, GPCRs interact with G proteins. They're coupled with G proteins. Now, it's important to talk a little bit about the structure of G proteins also. G proteins, in general, interact with G protein are here. As the name implies, GPCRs interact with G proteins. They're coupled with G proteins. Now, it's important to talk a little bit about the structure of G proteins also. G proteins, in general, are specialized proteins which have the ability to bind GTP and GDP. In other words, they are able to bind guanosine triphosphate and guanosine diphosphate, hence the name G proteins. Now, some G proteins are small proteins with a single subunit. However, when we talk about GPCRs, all G proteins that associate with GPCR are heterotrimeric. Meaning that they have 3 different subunits, 3 sections. So I'm going to go ahead and draw this out. The first section we call the alpha subunit. The first subunit or section of this protein we call the alpha subunit. The second we call beta. And the third we call gamma. So all 3 of these together, our alpha, beta, and gamma subunits together is our G protein. You'll notice that I drew the alpha and gamma subunits with a little tail-looking thing in our cell membrane. And the reason why is because these are the 2 subunits, our alpha and gamma, which are attached to the cell membrane by what we call lipid anchors. Now, the final thing about this picture that I need to draw in is our GDP or GTP. As you remember, the whole point of a G protein is because it binds GTP or GDP. Right now, this protein is inactive, and so it binds GDP, guanosine diphosphate. This GDP binds GDP, guanosine diphosphate. This GDP binds to the alpha subunit. When this protein becomes activated, and we'll talk in just a second how that happens, it will actually bind GTP instead. We'll talk in binds GDP, guanosine diphosphate. This GDP binds or GDP. Right now, this protein is inactive, and so it binds GDP, guanosine diphosphate. This GDP binds to the alpha subunit. When this protein becomes activated, and we'll talk in just a second how that happens, it will actually bind GTP instead. So now that we've drawn out our actual picture of our G protein, let's talk a little bit about how our signaling pathway actually happens. That's the whole point of membrane receptors, is that they respond to signaling molecules and ligands, and they respond to the environment. So, as we mentioned before, G protein coupled receptors interact with a wide variety of molecules on the outer surface of cells. Each receptor binds to usually one or just a few very specific molecules, fitting together like a lock and key. So if we pretend that our signaling molecule is a circle like this, the shape in which it should bind to the GPCR should be complementary. When this green signaling molecule binds to our GPCR will actually undergo what we call a conformational change. The shape of this GPCR will change, which in turn triggers a complex chain of events, which will ultimately influence different cell functions. So as we mentioned, our first step here is, of course, the ligand, the signaling molecule, has to bind to our GPCR. Once this ligand binds, our GPCR is going to undergo a conformational change. So let's just go ahead and redraw our GPCR. Again, 1, 2, 3, 4, 5, 6, 7, our 7 alpha helices. Now it's a little tougher to draw a conformational change, but the protein is actually going to look completely different. So here, because of this binding, we're going to bind GTP in lipid anchors. Now, the final thing about this picture that I need to draw in is our GDP or GTP. As you remember, the whole point of a G protein is because it binds GTP or GDP. Right now, this protein is inactive, and so it binds GDP, guanosine diphosphate. This GDP binds to the alpha subunit. When this protein becomes activated, and we'll talk in just a second how that happens, it will actually bind GTP instead. So now that we've drawn out our actual picture of our G protein, let's talk a little bit about how our signaling pathway actually happens. That's the whole point of membrane receptors, is that they respond to signaling molecules and ligands, and they respond to the environment. So as we mentioned before, G protein coupled receptors interact with a wide variety of molecules on the outer surface of cells. Each receptor binds to usually one or just a few very specific molecules, fitting together like a lock and key. So if we pretend that our signaling molecule is a circle like this, the shape in which it should bind to the GPCR should be complementary. When this green signaling molecule binds to our GPCR will actually undergo what we call a conformational change. The shape of this GPCR will change, which in turn triggers a complex chain of events, which will ultimately influence different cell functions. So as we mentioned, our first step here is, of course, the ligand, the signaling molecule, has to bind to our GPCR. Once this ligand binds, our GPCR is going to undergo a conformational change. So let's just go ahead and redraw our GPCR. Again, 1, 2, 3, 4, 5, 6, 7, our 7 alpha helices. Now it's a little tougher to draw a conformational change, but the protein is actually going to look completely different. So here, because of this binding, we're going to have a conformational change. The protein conformation of the GPCR will alter. Okay, so let's just write out our first 2 steps real quick. So step 1, we have the ligand binds to our GPCR. Step 2, we said that we undergo a conformational change. So our GPCR undergoes conformational change. What happens next is, because of this conformational change, our alpha subunit, which I'm going to draw in here, is actually going to exchange this GDP for GTP. So just keep track. Step 3, our alpha subunit exchanges GDP for GTP. So the molecule is swapped out. Instead of GDP, we have GTP. Now, because we have GTP bound to this alpha subunit, it'll now cause our alpha subunit to dissociate and move away from our beta and gamma subunit. Now, once this happens, these 2 different sections, our alpha subunit and our beta gamma dimer, these 2 together, are actually going to find a protein in the membrane. It's going to alter and regulate the function of that protein. So these 2 together are actually going to find a protein in the membrane. It's going to alter and regulate the function of that protein. So we could have another protein, for example, here, that the alpha subunit will find and regulate the function. So let's go ahead and write this out. Step 4, our alpha subunit dissociates and regulates target proteins. Now, during this step, there are a few things I like to note. The first is that both the alpha subunit and the beta gamma dimer can interact with other proteins to relay messages. We're going to focus in on the alpha subunit because it tends to be more common and more. However, the beta gamma subunits can still regulate functions of other proteins. The target proteins can be enzymes that produce second messengers, which we'll talk a little more about in a second, or ion channels that also tends to be more common and more. However, the beta gamma subunits can still regulate functions of other proteins. The target proteins can be enzymes that produce second messengers, which we'll talk a little more about in a second. Proteins can be enzymes that produce second messengers, which we'll talk a little more about in a second, or ion channels that also let ions be second messengers. Now, as we mentioned, G proteins are incredibly diverse. Some G proteins can stimulate activity while others can also inhibit. Now, step 5, once this alpha subunit activates a target protein, this target protein can then function. So let's boil going to a subunit. Now, change our alpha subunit, which I'm going to draw in here, is actually going to exchange this GDP for GTP. So just keep track. Step 3, our alpha subunit exchanges GDP for GTP. So the molecule is swapped out. Instead of GDP, we have GTP. Now, because we have GTP bound to this alpha subunit, it'll now cause our alpha subunit to dissociate and move away from our beta and gamma subunit. Now, once this happens, these two different sections, our alpha subunit and our beta gamma database. Instead of GDP, we have GTP. Now, because we have GTP bound to this alpha subunit, it'll now cause our alpha subunit to dissociate and move away from our beta and gamma subunit. Now, once this happens, these two different sections, our alpha subunit and our beta gamma dimer, these two together, are actually going to find a protein in the membrane. It's going to alter and regulate the function of that protein. So we could have another protein, for example, here, that the alpha subunit will find and regulate the function. So let's go ahead and write this out. Step 4, our alpha subunit dissociates and regulates target proteins. Now, during this step, there are a few things I like to note. The first is that both the alpha subunit and the beta gamma dimer can interact with that. Now, subunit dissociates and regulates target proteins. Now, during this step, there are a few things I like to note. The first is that both the alpha subunit and the beta gamma dimer can interact with other proteins to relay messages. We're going to focus in on the alpha subunit because it tends to be more common and more. However, the beta gamma subunits can still regulate functions of other proteins. The target proteins can be enzymes that produce second messengers, which we'll talk a little more about in a second, or ion channels that also let ions be second messengers. Now, as we mentioned, G proteins are incredibly diverse. Some G proteins can stimulate activity while others can also inhibit. Now, step 5. Once this alpha subunit activates a target protein, this target protein can then relay a signal. As long as this ligand is bound to the GPCR, this process where our alpha sub-target protein, this target protein can then relay a signal. As long as this ligand is bound to the GPCR, this process where our alpha subunit dissociates, looks for a protein, and regulates that target protein, causing a whole chain of events, can happen repeatedly as long as this ligand is bound. Now, how can we actually make this thing go back to normal?
All right, we got 10 minutes. 10-minute breakarino. Geronimo. Yeah. How can we go back to normal? Well, you're gonna have to get rid of the ligand. Text session. No. Why is this guy not here? What the heck? Oh. Okay, let's see what they say. Let's see what he says. Yeah. All right, I'm gonna take a break. I'll be back, guys. Dang, how long have I been muted for? Well, that sucks. I don't know if you guys even heard anything anyways. Oh, man. Oh, well. Are you guys at least seeing? Yeah, you guys are seeing. Not really that good though. Is that better? Control flowing. Sort of. That looks pretty good. It's only specific type. It's also pretty specific. It's also pretty specific. I know they. Yeah, it's a receptor. Specific. So you have to have a specific receptor. So it's pretty good. Okay. Oh, but it's like it's true. The medication, the medication is not going to be a receptor. So that's actually out. So it needs to be a ligand. It needs to be a ligand. We got to be a specific ligand. We do need to be a specific receptor, though. It's kind of true. C makes sense, and I think any of that. Oh shoot! Oh, let's see. Let's go. That's true. This isn't really tell us anything. But I don't know. I'm thinking between A and C. I'm gonna go with A. Oh, stretch activated. Oh, stretch. Oh, never mind. Stretch activated cardiac song. I don't know. We didn't really talk about that. That's not true. Enhancing their bonds. Well, I think A is like better worded. So I think we'll go with A. Oh, then it's B. Ooh. A locked in key interaction. Well, that's already what's happening. Oh, I should have gone with A. Oh, that's a different model, right? Okay. Gotcha. I really like doing this because it's kind of what is done in the other one anyways. It's not true. Lion gated ion channels. Ligand gated. You said it was a secret giant bee one. Or maybe it could have been this one. Either it was cyclic KMP or adenylene, but it wasn't B or D. Maybe it's A. Was it A? Oh, okay. Okay, yeah. I think it was B. Maybe it's B. I'm thinking D. I'm not too sure what these are. So we're talking about muscle tissue. We're doing EQ, we would have like a bundle said. I don't know about this though. I would process I would think that this would be for decolorization. Maybe B. I'm thinking D. Then I might go with C. Oh no, I'm not sure. Maybe A. Heat 1. Wait, what? I mean, I would go 8 and 2, right? Hormone volumes to PCL. Maybe we started with 1. It was not definitely not going to start with 2. And know how I can start with 8 actually. So 1, 5. So 1, 5. GTP. Then 1, 5, and then 7. And 3. Phosphorylation cascade. Oh, 7? I'm in 6. whatever it is, it's D, right? Least likely. Well, something big. Whatever, just something big. Growth hormone, probably something big as well. My thing was C2H4. Oh, that's a good question. I mean, this guy's already pretty non-polar. I don't know why he needs any help. What does he need help to do? He just passed that through pretty quick. Yeah, I'm not sure on this one, to be honest. I'm gonna go with a large molecule like estrogen. I go with the growth hormone. Oh, whoops. The keyword right there, intracellular. Oh my goodness. Yeah, okay. Gotcha. This makes sense. Let me think. I don't know what that means. Multiple signal transition pathways? I think it wasn't just one. Wasn't G's coupled also a little bit specific? Or was it? Maybe not. I don't think it's like everything. I don't know. I don't think it's like that's diverse. Okay. Hmm. This camp. I think I've never seen this camp anyways. The first messenger is epinephrine. Yeah, that's what I thought. So we don't want type enzymes on the move. I don't know what they intercalated this for. I don't think so. I haven't given it over. And this is for structure. So I think it's going to be good. This single layer cells. Maybe individual. Oh, actually tight junctions? What the heck? What the heck? How is it single layer of cells? Single layer of cells. Oh, maybe I'm just confusing. Oh, I think that was something else. Oh, I think I know why. Are they the same thing or not? What? I think that's where I got confused. It's the same thing. That's why I got confused. I'm like, what? What is it talking about with the plasma membrane? It's the same thing. Okay, sure. Gotcha. I was like, what the heck? I thought it was talking about something different. That actually confused me quite a bit. Anyways, yeah, I think I would have gotten it right if I didn't have that confusion then, because she's trying to say single layer of cell. Single layer of cells. Mm-hmm. A single layer of cells. A single layer of cells. Okay. Zero hormones are just a social nitrogen on target cells. That's a good question, actually. Steroid hormones. It's phosphorylation cascading with testosterone. This would make sense. Enzymes? Enzymes don't modify steroid cell. Let's see. Huh. Ooh. Okay. Cell interactions, huh? What's next? Transport across a cell membrane. Cytoskeleton. Oh, I just want to take a look at this real quick. Not this one. Let's just take a look at the end of it real quick.
Formation of the cell membrane. External signals. It's in the cytoplasmic membrane. These membrane receptors
Mm-hmm. Okay. What's the next one? Transport. Oh, we also have to do eukaryotic cells today too. What the heck? That was literally just one article, and then it's all videos. Hold on. Let me check if he texted. Maybe I texted him too late, huh? Oh, I think I just texted him too late. Okay, never mind. We're okay. Oh. Timer's not starting. What the heck? Seriously? Again, man? and type 2 diabetes mellitus. Oh, oh. Okay. Oh. Cardiomyocyte. Hmm. Hmm.
The cell in our bodies, the cell is the smallest unit of life. And just like larger units of life, like the entire human body, the cell needs nutrients that are at times available outside of their cell membrane. And they also make waste products that they need to get outside in order to survive. And so, an important function of living is the ability to transport things, across a cell membrane, transport things across a cell membrane. And so in the next couple of videos, we're going to talk about these different types of transport mechanisms. In this video in particular, I'll give you an overview of the different types before we go into detail. And a good rule of thumb to have in the back of your head as we talk about this is that the bigger the passenger, or the bigger the waste product or the nutrient that we're going to be talking about that we need to transport across our cell membrane, that means the bigger the car that we're going to need to get them across. And so you'll see that as we go in order right here, from the smallest solutes or nutrients or waste products to the largest things that we transport across our cell membrane. We've got specialized mechanisms to make these things move. So the first example of a transport mechanism I want to talk about
is just a simple potassium leak channel. So I'll call this a potassium leak channel. And you might be wondering, well, why do we call it a leak channel? Why do we just call it just a regular channel? Well, the reason is that potassium has a large concentration inside of our cells. In fact, there are more potassium ions that are found inside of our cells than there are outside of our cells. And this is the exact opposite of what we see compared to sodium. For sodium, there's a ton of sodium ions that hang out outside of the cell. So they have a large concentration here, and there's a smaller portion of them that are located inside of the cell. So when there's an open channel or an open gate present, potassium naturally wants to flow down its concentration gradient to go outside of the cell. And this type of transport mechanism is called passive transport. Passive transport. And we'll talk about another mechanism in a moment that's called active transport. So why do we call this passive? Well, the reason we make this distinction is because no energy was used in order to allow our potassium ion to transport across the membrane. Now, at this point, I also want to mention that there are a couple of different flavors of passive transport we'll talk more detail about. There's something that's called diffusion, which is the movement of solutes in space, and we'll talk about that, what that means. There's osmosis that relates mainly to the movement of water, and then there's also filtration. We'll talk about filtration as it occurs in the kidney. And then finally, there's also what's called facilitated diffusion. Facilitated diffusion, which unlike diffusion, as I've listed above, facilitated diffusion utilizes the help of a protein channel, which is exactly what we talked about right here. So this is facilitated diffusion that I gave you the example of for the potassium leak channel. Now, the other thing you should be asking yourself is, how is it that we had a large concentration of potassium in the cell in the first place, or a large concentration of sodium outside of the cell? Well, the honest answer is that there was energy that was used to set up that ion gradient. And so here we go, we're going to move towards a bigger concept here, where instead of just moving one ion across, we're going to move two at the same time. And truth be told, it's a little more complicated than that, but just to simplify it for now, we're going to talk about a process that allows for sodium to be pushed against its concentration gradient, to be kicked out of a cell fusion, which, unlike diffusion, as I've listed above, facilitated diffusion utilizes the help of a protein channel, which is exactly what we talked about right here. So this is facilitated diffusion that I gave you the example of for the potassium leak channel. Now, the other thing you should be asking yourself is, how is it that we had a large concentration of potassium in the cell in the first place, or a large concentration of sodium outside of the cell? Well, the honest answer is that there was energy that was used to set up that ion gradient. And so here we go, we're going to move towards a bigger concept here, where instead of just moving one ion across, we're going to move two at the same time. And truth be told, it's a little more complicated than that, but just to simplify it for now, we're going to talk about a process that allows for sodium to be pushed against its concentration gradient, to be kicked out of a cell to a place where there's already a bunch of them hanging out, as well as potassium moving from a place where it's very comfortable and happy into this area where there's already a high concentration of potassium ions. So this is not the direction these ions want to flow. Right. So in fact, we're going to need a little bit of energy to make that happen. And so that energy is in the form of ATP. So that's adenosine triphosphate, which is broken into adenosine di, as in 2-phosphate. And there's a little phosphate group that broke off here as well. This protein is affectionately called a sodium, listed above, facilitated diffusion, facilitate movement of water. And then there's also filtration. We'll talk about filtration as it occurs in the kidney. And then finally, there's also what's called facilitated diffusion. Facilitated diffusion, which, unlike diffusion, as I've listed above, facilitated diffusion utilizes the help of a protein channel, which is exactly what we talked about right here. Okay. So this is facilitated diffusion that I gave you the example of for the potassium leak channel. Now, the other thing you should be asking yourself is, how is it that we had a large concentration of potassium to be kicked out of a cell
Sure.
to a place where there's already a bunch of them hanging out, as well as potassium moving from a place where it's very comfortable and happy into this area where there's already a high concentration of potassium ions.
Right.
So this is not the direction these ions want to flow.
Right.
So in fact, we're going to need a little bit of energy to make that happen. And so that energy is in the form of ATP. So that's adenosine triphosphate, which is broken into adenosine di, as in 2-phosphate. And there's a little phosphate group that broke off here as well. This protein is affectionately called a sodium-potassium pump. A sodium-potassium pump. And in some books, you'll see it called a sodium-potassium ATPase, because you break a molecule of ATP to use it.
Oh.
And this is an excellent example of something that's called active transport. Active transport. And as the name suggests, relative to when we talked earlier about passive transport, active transport uses energy. And it uses energy in this scenario by breaking a molecule of ATP. Now, as sort of a side note here, this is specifically known as primary active transport because we've directly used ATP here. So a direct use of ATP is primary active transport, which may lead you to ask, well, are there other types of active transport as well?
Yeah.
And the answer to that question is yes, you are absolutely correct. And I'll give you an example from the gut. So in the gut, when we eat things, like salty food might have some sodium in it, or it might be sweet food, and it's got some glucose in it as well. And as you already know, there's a lot of sodium that's outside of our cells in the extracellular space. Well, our intestines, our guts, are lined with things that are called enterocytes, and they're just basically cells of the GI tract. And they're just like normal cells where they want sodium to enter. So this protein that's on our enterocyte here will let sodium enter, but because we're in the gut, another magical thing happens. This glucose molecule will enter as well. And this is an example of something that's called symport. Symport, where both molecules are moving in the same direction. One where we're using sodium to flow down its ion gradient, and then glucose going from outside of the cell into the cell. It's basically coming along for the ride, which is why this is a great example of what's called secondary active transport. Secondary, meaning that we used energy. Certainly we use energy here, so I'll say it uses energy here, but not directly. This, in fact, uses a gradient that was already set up. So a gradient set up using energy.
It uses the primary.
And so in that sense, it's indirectly using our ATP molecule or indirectly using our energy that generated this sodium gradient. And so that's what happens when we
From the primary, right? I mean, yeah, from the primary.
have our sodium and our glucose absorbed into our intestine. After it's absorbed into our enterocytes, they actually need to go to our bloodstream. So I'll draw a little blood vessel right here. That's where our nutrient that generated this sodium gradient. And so that's what happens when we have our sodium and our glucose absorbed into our intestine. After it's absorbed into our enterocytes, they actually need to go to our bloodstream. So I'll draw a little blood vessel right here. That's where our nutrients need to go to flow elsewhere in our body. And in order to get out of our enterocyte and end up in our bloodstream, we actually use the same type of channel to help our glucose molecule that just entered our enterocyte to leave the cell and travel to this blood vessel or this capillary. And what's unusual is that, again, sodium is in play here, but this time it's actually going in the opposite direction. But this completely makes sense. Remember, there's a higher concentration of sodium outside of our cells, and so it naturally wants to flow down its ion gradient into the cell. And still, this is an example of secondary active transport, but instead of symport, now we have what's called antiport. Antiport because our two molecules are moving in the opposite direction of each other. And we'll talk again about secondary active transport in a part of the kidney called the nephron. For now, let's talk about bigger molecules trying to cross the membrane. As you see, we've been getting progressively larger from 1 ion to 2 ions. Now we're talking about a bigger molecule like glucose. What about if we have a giant protein that wants to enter the cell? What I've drawn here is not the protein. Instead, I'll draw the protein inside of here. I'll just write AA, because you know proteins are made of amino acids. So there's a couple of amino acids in here that want to enter our cell. This guy is a vesicle. A vesicle is just a small pocket of cell membrane that's surrounding some type of cargo or some type of thing we're trying to transport. In this case, it's this protein. And remember, it's the exact same membrane we have around our cell. And once this vesicle gets close enough to our membrane right here, it'll actually fuse. And in doing so, will then create an opening from the inside of the vesicle, connecting it to the inside of our cell, which means that our
Inward folding of that plasma membrane.
amino acid can actually enter inside. These steps that we saw here as we went from here to allow our amino acid to enter the cell is a process that's called endocytosis. Endocytosis, which, as you can see here, means for something to go into a site or a cell. And because we're moving something larger than what we talked about before, this uses a lot of energy, directly here to make this process happen.
Not ATP.
And you can actually have the opposite case as well, where a vesicle that's made inside the cell, as we'll talk about, sometimes will be made off of what's called the Golgi apparatus, and that's an organelle within your cell. It'll create uses a lot of energy directly here to make this process happen. And you can actually have the opposite case as well, where a vesicle that's made inside the cell, as we'll talk about, sometimes will be made off of what's called the Golgi apparatus, and that's an organelle within your cell. It'll create a vesicle that'll have some protein that we want to get rid of. And I want to make this different. So instead of amino acids in here, I'll write ACH, or acetylcholine, which is a type of neurotransmitter we have in our body. So once this vesicle with acetylcholine is made from the Golgi apparatus, it floats towards our cell membrane, similar to how we saw earlier. And then these membranes will fuse, the membrane of our vesicle as well as the membrane of our cell, causing the acetylcholine to be kicked out. So this process where this vesicle came here and then caused the acetylcholine to get out of our cell is called exocytosis, which is why I call it the opposite of endocytosis, because something is exiting our site or a cell. And this is similar to endocytosis in that it uses a lot of energy to happen. So these are all the main processes or mechanisms we use to move things across our cell membrane. And they're very important to understand. Just to give you kind of an idea why, when things are wrong with our proteins or when viruses hijack some of the mechanisms that we use to move things across our membrane, bad things can happen. So the more we know here, the better we can fight a lot of our different infectious diseases.
Well done. Thank you so much. All right, let's take a 10-minute. It's only gonna take us 3 days. Oh, I'm only gonna do 4 today and 4 tomorrow. 4 today and 4 tomorrow. And then I think we're caught up because 2, 4, 6, 8. 4 today and 4 tomorrow. 8. 2, 4, 6, 8. That should be on 10, but tomorrow will be on 8. Oh, actually, I need to do 4 today, 4 Thursday, and 4 Friday. Huh? Yeah, we're basically doing 4 all the way through until Friday. And then Saturday. Well, Saturday leaves us with just these, which is pretty nice. And that's nice, just have these, and then we're back on track. We're back on track, and it's only two every day. Oh, that'd be so nice. 2 every day, but I have to push the exam back one week, which I'll do, whatever. Okay, set up the next video. I have to do that, but I have time. Alrighty then. We got, yeah, I don't know, however long it's gonna take us to get through this one. And well, this one here, huh? It has cell theory here, so I'm guessing we're just gonna do. I'm not gonna be so slow with this. I guess I was doing some here from I don't know when, but we'll do those and we'll do this one. Might as well hit this one too, and we'll hit. Well, we already did this one. Diffusion, cellular respiration. Maybe we just keep going until we hit cellular respiration. Yeah, I think that'll be cell theory. I don't know. It's not there, so there's no real part of cell theory, you know. We'll just count that as cell theory, and then we'll do, eukaryotic cells, and then we'll be done for today. Well, and then we'll do Anki, right? Anki, and then we'll read the high yield, and then we'll read the high yield. Yeah, something like that. Anyways, and I have to add the cards. Today is gonna be a good day, great day. We'll do 4, and we'll finish it off. It'll be a good day. Today's gonna be a good day.
Dang, it's so hot. Nice and quiet, listeners. This worked out. I want to make sure we finish. We want to finish today. Let's work out a little bit. Need to, you know. I kind of want to try and hit different things too. I should do some. Do a couple push-ups or something. Let's take a 15 here. I should have just taken it earlier. Whatever. Take a 15. Get a quick workout in. We'll do it. Do another workout around 8 or something. We might finish it at 10, which is okay. That's what we kind of expected. But we'll do better. We'll do better. Always about doing better, you know. What can you do? What can I say except you're welcome?
Oh, we gotta set a timer. Right. I'm gonna work out for hours. I'm gonna work out for hours. Quick. Hello? Hold on, guys. I think maybe it's my mom.
You want some food, Papa?
Oh, you're a sweeter? I thought you were banging for a reason. What are you banging for?
No, I was just to see how strong or hollow the wall is.
Oh, okay. Thank you. All right, let's do 2 more sets of 10. And then let's do like 40 more squats, and we'll call it. I lost my grip. That music choice was really bad. Whatever. You got it done. All right, thank you. Look at me, I'm like freaking drenched. Drenched, bro. I'm drenched in sweat, bro. Bro. Anyways, let's go and put everything back. Oh, it's always still there, bad. Alright, switch back. Let's see. Let's finish this up, you know. I really want to finish this up. Such a back stretcher, dude. At least the one type of workout, plus I should probably try and specialize it. All right, we're back. Let's just continue while I eat. I got my Gigantor. I swear, I think this is actually making me gain weight. Well, plus just setting down so much. But I don't want to be, I just don't want to be unhealthy, really overweight by the time I get to BMT. Because I'm not really doing any running, Like, that's the thing, I'm not doing any running. Yeah, it's nice. I'm not doing any running, but I can at least do some type of cardio here. At least do some type of cardio. Even though I'm not running. I think that's important.
To talk about passive transport. All right, so in this video, we're going to talk about passive transport. So let's start off taking a look at a cell. So there's a cell right there, and why don't we just zoom in up here? And let's focus in on the membrane. And as you know, it's a lipid bilayer, which basically means that we have these hydrophilic heads that are sitting over here. So I'll draw just a few of them. So 3 of them right here, and then 3 of them right here as well. And they've got hydrophobic tails. These are fatty acid tails that come down like this. So they are kinked like that, and that's what makes the hydrophobic core of our lipid bilayer. And I can go on and draw this all the way, but I'm just going to have this blue outline as our hydrophilic head. Down here as well, hydrophilic head, and the hydrophobic tail is inside this gray area. And so the question arises then, when we have a small particle, let's say this is a chloride ion, Cl negative, that's sitting right there, how do we get it from the outside area, the extracellular space, so I'll say out, this is from the outside to the inside right here. And in our gut, which is where this example is going to take place, we do that by passive transport. And as we talked about earlier, there are 4 different types of active transport. And the main type we're going to focus on in this video is what's called facilitated diffusion. Facilitated diffusion. Because we're diffusing or we're moving across a certain space. But the question here is, what's facilitating that movement? And therein lies the answer of what we're going to focus on for this video. So along our cell membrane, there are also going to be proteins that are embedded along the cell membrane. And so what's going to facilitate the movement of this chloride ion across from the outside to the inside is this chloride channel right here. And so this channel is built in a funny way that has this little pocket that sits right there and is shaped like that. And the idea behind this pocket is that it's the site where chloride, and specifically chloride, can sit down. So if I were to go through and draw it sitting in here, it would look a little bit like this. Not too different from what I just drew, but there's a very important distinction that we're going to have to make here. And what happens is that now that our chloride is sitting here, we've made this chloride channel right here uncomfortable. Now we're uncomfortable. It doesn't want to sit like this now, because now that we're holding the chloride ion, we want to change our posture. And so what happens is that our chloride ion will actually snap and change its shape. And it'll snap in such a way that it'll flip. And when it flips like this, what you'll notice is that the part that was holding on to our chloride will now suddenly be facing the intracellular face of our cell membrane, which sure enough means that the chloride ion can now leave, leaving behind then the same protein that we started off with right here, but now it's a little different. Now, as you can see, it's got the same shape, but instead it's clearly missing our chloride ion. And so what's happened along the way is that when we made this switch here from this uncomfortable shape to this relatively more comfortable shape, it allowed our chloride to exit. And now that it's exited into the inside of our cell, our protein has become uncomfortable again. And so now that it's uncomfortable, it needs to shift. And when it shifts, what shape do you think it's going to take? I think you probably guessed it. It's going to look exactly like what the protein did before it made contact with the chloride in the first place. And so now it's comfortable again. So it's sitting nice and comfy. It's nice and comfy. And in fact, it's ready to take on another chloride ion. And so what our protein is doing along the way is that it's changing its conformation. And the conformation is just the pose the protein is taking. And it changes its conformation, whether it's binding the chloride ion, as it did here to become more comfortable, or if it's not holding the chloride ion, as it did here when it was uncomfortable, to shift always to a more comfortable position. And through this process, in a very stepwise way, our chloride ion is able to enter the cell without using any energy whatsoever. No ATP is used at all. Instead, this protein is used to facilitate the movement of the chloride into the cell.
I don't think we'll take any more breaks. We took the money.
In this video, I want to cover several topics that are all related. And on some level, they're really simple, but on a whole other level, they tend to confuse people a lot. So hopefully we can make some headway. So a good place to start, let's just imagine that I have some type of container here. Let's say that's my container. And inside of that container, I have a bunch of water molecules. It's just got a bunch of water molecules. They're all rubbing against each other. It's in liquid form. This is liquid water. And then inside of the water molecules, I have some sugar molecules. Maybe I'll do sugar in this pink color. So I have a bunch of sugar molecules right here. I have many, many more water molecules, so I want to make that clear. I have many, many more water molecules in this container we're dealing with. Now, in this type of situation, we call the thing that there's more of, the solvent. So in this case, there's more water molecules, and you can literally just view more as the number of molecules. I'm not going to go into a whole discussion of moles and all of that because you may or may not have been exposed to that yet, but just imagine whatever there's more of, that's what we're going to call the solvent. So in this case, water is the solvent. And whatever there is less of, so the more, water is the solvent, and in this case, that is the sugar, that is considered the solute. This is the solute. So the sugar doesn't have to be sugar. It could be any molecule that there's less of in the water in this case. Sugar is the solute. And we say that the sugar has been dissolved into the water. Sugar has been dissolved into the water. And this whole thing right here, the combination of the water and the sugar molecules, we call a solution. We call this whole thing a solution. And a solution has a solvent and a solute. The solvent is water. That's the thing doing the dissolving. And the thing that is dissolved is the sugar. That's the solute. Now, all of this may or may not be review for you, but I'm doing it for a reason because I want to talk about the idea of diffusion. Diffusion. And the idea is actually pretty straightforward. If I have, let's say the same container. Let me do a slightly different container here. Just to talk about diffusion, we'll go back to water and sugar, especially back to water. Let's say we have a container here. And let's say it just has a bunch of, let's say it just has some air particles in it. It could be anything, oxygen or carbon dioxide. So let me just draw a couple of air molecules here. So let's say that is a gaseous, just for the sake of argument, gaseous oxygen. So each of this is an O2, each of those, right? And let's say that this is the current configuration, that all of this is a vacuum here, and that there's some temperature. So these water molecules, they have some type of kinetic energy. They're moving in some type of random directions right there. So my question is, what is going to happen? What is going to happen? Each of this is an O2, each of those, right? And let's say that this is the current configuration, that all of this is a vacuum here, and that there's some temperature. So these water molecules, they have some type of kinetic energy. They're moving in some type of random directions right there. So my question is, what is going to happen? What is going to happen in this type of container? Well, any of these guys are going to be randomly bumping into each other. They're more likely to bump into things in this down left direction than they are in the upright direction. So if this guy was happening to go in this down left direction, he's going to bump into something and then ricochet into the upright direction. But in the upright direction, there's nothing to bounce into. So in general, everything is moving in random directions, but you're more likely to be able to move in the rightward direction. When you go to the left, you're more likely to bump into something. So it's almost common sense. Over time, if you just let this system come to some type of equilibrium, and I'm not going to go into detail on what that means. You can watch the thermodynamics videos if you'd like to see that. You'll eventually see the container will look something like this. I can't guarantee it. There's some probability it would actually stay like this, but very likely that those 5 particles are going to get relatively spread out. This is diffusion. And so it's really just the spreading of particles or molecules from high concentration to low concentration areas. Right? In this case, the molecules are going to spread in that direction from a high concentration to low concentration area. And you're saying, Sal, what is concentration? And there's many ways to measure concentration, and you can go into molarity and molality and all of that. But the very simple idea is, how much of that particle do you have per unit space? So here you have a lot of those particles per unit space, and here you have very few of those particles per unit space. So this is a high concentration, and that's a low concentration. So you can imagine other experiments like this. You could imagine a solution like, let's do something like this. Let's say I have 2 containers. Say 2 containers. Let's go back to the solution situation. This was a gas, but I started off with that example. So let's stay with that example. Let's say that I have a door right there that's larger than either the water or the sugar molecules. On either side, I have a bunch of water molecules. I have a bunch of water molecules on either side, just like that. On either side. So I have a lot of water molecules. So if I just had water molecules here, they're all bouncing around in random directions. And so the odds of a water molecule going this way equivalent to odds of a water molecule going that way, assuming that both sides have the same level of water molecule, otherwise the pressures would be different. But let's say that, the top of this is the same as the top of this. So there's no more pressure going in one direction or another. So, if for whatever reason, a bunch more water molecules were going in the rightward direction, then all of a sudden this would fill up with more water. And we know that isn't likely to occur. So this is, this is just a solution this is just a kind of 2 containers of water. Now let's put some solute in it. Let's dissolve some solute in it. Let's say we do all the dissolving on the left-hand side. So we put some sugar molecules on the left-hand side. And these are small enough to fit through this little pipe. That's one assumption that I'm making. So what's going to happen? All of these things have some type of kinetic energy. They're all bouncing around. Well, over time, the water is going back and forth. This water molecule might go that way, that water molecule might go that way, but they net each other out. But over time, one of these big sugar molecules will be going in just the right direction to go through. Maybe this guy's going in that direction. He starts off going in that direction. He goes just through this tunnel connecting the 2 containers, and he'll end up there, right? And this guy will still be bouncing around. There's some probability he goes back, but there's still more sugar particles here than there. So there's more probability that so this guy's on that side. So let me cross him out. There's still more probability that one of these guys will go to that side, than one of these guys will go to that side. So you can imagine if you're doing this with gazillions of particles. I'm only doing it with 4. Over time, the particles will have spread out so that their concentrations are roughly equal. So that maybe you'll have 2 here over time. But if you're when you're only dealing with 3 or 4 or 5 particles, there's some probability it doesn't happen. When you're doing a gazillion and they're super small, it's a very, very, very high likelihood. But anyway, this whole process, we went from a container of high concentration to a container of low concentration, and the particles would have spread from the low concentration container to the high concentration container. So they diffused. This is diffusion. This is diffusion. And just so that we learn some other words that tend to be used with the idea of diffusion, when we started off, this had a higher concentration. The left-hand side container had higher concentration. Higher concentration. It's all relative, right? It's all higher than this guy. Higher concentration. And this right here had a lower concentration. Lower concentration. And there are words for these things. This solution with a high concentration is called a hypertonic solution. Let me write that in yellow. Hypertonic solution. Hyper, in general, meaning having a lot of something, having too much of something. And this lower concentration is hypotonic solution, lower concentration. You might have heard maybe one of your relatives, that they haven't had a meal in a while, say, I'm hypoglycemic. That means that they're feeling lightheaded. There's not enough sugar in their bloodstream and they want to pass out, so they want a meal. If you just had a candy bar, maybe you're hyperglycemic, or maybe you're just hyper in general. But so these are just good prefixes to know. But hypertonic, you have a lot of the solute, you have high concentration, and then in hypotonic, not too much of the solute, so you have a low concentration. These are good words to know. So in general, diffusion, if there's no barriers to the diffusion like we had here, you will have the solute go from a high concentration or hypertonic solution, if they can travel, to a hypotonic solution, to a hypo where the concentration is lower. Now, let's do an interesting experiment here. We've talked about diffusion, and so far we've been talking about the diffusion of the solute, right? And in general, and this is not always the case, if you want to be as general as possible, the solute is whatever you have less of, the solvent is whatever you have more of. And the most common solvent tends to be water. But it doesn't have to be water. It could be some type of alcohol. It could be it could be mercury. It could be a whole set of molecules. But water in most biological or chemical systems tends to be the most typical solvent. It's what other things are dissolved into. But what happens if we have a tunnel where the solute is too big to travel, but water is small enough to travel? So let's think about that situation. Let's think about that situation. In order to think about it, I'm going to do something interesting. Let's say we have a container here.
I'm lagging.
Let's say we have, actually I won't even draw a container. Let's just say we have an outside environment that has a bunch of water. This is the outside environment. And then you have some type of membrane. You have some type of membrane here. That's a membrane. Water can go in and out of this membrane. So it's semi-permeable. Well, it's permeable to water, but the solute cannot go through the membrane. So let's say that the solute is sugar. So we have water on the outside and also inside the membrane. So these are little small water molecules. This is a membrane right here. And let's say that we have some sugar molecules. I'm just picking on sugar. It could have been anything. So we have some sugar molecules here that are just a little bit bigger, or they could be a lot bigger. Actually, they're a lot bigger than water molecules. So you have a bunch of, and I only draw 4, but you have a gazillion of them, right? But you have that much more water molecules. I'm just trying to show you have more water molecules than sugar molecules. And this membrane is semi-permeable. Semi-permeable. Permeable means that it allows things to pass. Semi-permeable means it's not completely permeable. So semi-permeable in this context, I'm saying I allow water to pass through the membrane. So water can pass. Water can pass. But sugar cannot. Sugar is too large. Sugar cannot. And the reason why in this case is because the sugar molecule is too big. So if we were to zoom in on the actual membrane itself, maybe the membrane looks like this. I'm going to zoom in on this membrane. So I'm going to zoom in on this membrane. So it has little holes in the membrane, just like that. And maybe the water molecules are about that size, so they can go through those holes. So the water molecules can go back and forth through the holes, just like that. But the sugar molecules are about that big, so they cannot go through that hole. They're too big for this opening right here to go back and forth between them. Now, what do you think is going to happen in this situation? So first of all, let's use our terminology. Remember, sugar is our solute, water is our solvent, semi-permeable membrane. Which side of the membrane has a higher or lower concentration of solute? Well, the inside does. The inside is hypertonic. Hypertonic, so I can write here, hypertonic. The outside has a lower concentration, so it's hypotonic. It's hypotonic out here, lower concentration of solute. Now, if these openings were big enough, based on what we just talked about, these guys are bouncing around. Water is traveling in either direction and equal probability. Or I'm going to talk about that in a second. If everything was wide open, it would be equal probability. But if it was wide open, these guys eventually would bounce their ways over to this side, and you would probably end up with equal concentrations eventually. And so you would have your traditional diffusion, where high concentration of solute to low concentration of solute. But in this case, these guys, they can't fit through the hole. Only water can go back and forth. If these guys were not here, water would have an equal likelihood of going in this direction as they would be going in that direction. A completely equal likelihood. But because these guys are on the right-hand side of, or in this case, on the inside of our membrane, this is our inside of our membrane zoomed up, these guys, it's less likely, because these guys might be in the kind of the approach position of the holes, it's that slightly less likely for water to be in the approach position for the holes. So it's actually more probable that water could enter than water exit. And I want to make that very clear. If these sugar molecules were not here, obviously it's equally likely for water to go in either directions. Now that these sugar molecules are there, these sugar molecules might be on the right-hand side. They might be blocking, I guess the best way to think about it is blocking the approach to the hole. They'll never be able to go through the hole themselves, and they might not even be blocking the hole, but they're going in some random direction. So if a water molecule was approaching, it's all probabilistic, and we're dealing with gazillions of molecules. It's that much more likely to be blocked to get outside. But the water molecules from the outside, there's nothing blocking them to get in, so you're going to have a flow of water inside. So in this situation, with a semi-permeable membrane, you're going to have water, you're going to have a net inward flow of water. And so this is kind of interesting. We have the solvent flowing from a hypotonic situation to a hypertonic solution. But it's only hypotonic in the solute. That's when you talk about the solute. And it's only hypertonic when you talk about the solute. But water, if you flip it the other way, if you view sugar as the solvent, then you could say we're going from a high concentration of water to a low concentration of water. I don't want to confuse you too much. This is what tends to confuse people. But just think about what's going to happen. No matter what, in what situation, the solution is going to do what it can to try to equilibrate the concentration, to make the concentrations on both sides as close as possible. And it's not just some magic. It's not like the solution knows. It's all based on probabilities and these things bumping around. But in this situation, water is more likely to flow into the container. So it's actually going to go from the hypotonic side, when we talk about low concentration of solute, to the side that has high concentrations of solute, of sugar. And actually, if this thing is stretchable, more water will keep flowing in, and this membrane will stretch out. But we won't go into too much detail here. But this idea of water, of the solvent, if in this case water is the solvent, of water as a solvent diffusing through a semi-permeable membrane, this is called osmosis. Osmosis. You've probably heard learning by osmosis. If you put a book against your head, maybe it'll just seep into your brain. Same idea. That's where the word comes from. This idea of water seeping through, but this idea of solute, of sugar. And actually, if this thing will stretch out, but we won't go into too much detail here. But this idea of water, of the solvent, if in this case water is the solvent, of water as a solvent diffusing through a semi-permeable membrane, this is called osmosis. Osmosis. You've probably heard
learning by osmosis.
Learning by osmosis. If you put a book against your head, maybe it'll just seep into your brain. Same idea. That's where the word comes from. This idea of water seeping through membranes to try to make concentrations more equal. So if you say, well, you have high concentration here, low concentration here, if there was no membrane here, these big molecules would exit. But because there's this semi-permeable membrane here, they can't. So the system, just probabilistically, no magic here, more water will enter to try to equilibrate the concentration. Eventually, if maybe there's a few molecules out here, not as high concentration here. Eventually, if everything was allowed to happen fully, you'll get to the point where you have just as high a concentration on this side as you have on the right-hand side, because this right-hand side is going to fill with water and also probably become a larger volume. And then once again, the probabilities of a water molecule going to the right and to the left will be the same, and you'll get to some type of equilibrium. But I want to make it very clear. Diffusion is the idea of any particle going from higher concentration and spreading into a region that has a lower concentration and kind of just spreading out. Osmosis is the diffusion of water. And usually you're talking about the diffusion of water as a solvent. And usually it's in the context of a semi-permeable membrane where the actual solute cannot travel through the membrane. Anyway, hopefully you found that useful and not completely confusing.
Let's talk a little bit about exocytosis, which is how the cell is able to release larger molecules that might be used by the rest of the body, other cells, or maybe it's going to be part of the extracellular matrix. And to understand how this works, it's really the reverse of endocytosis. We're going to go and produce some protein in the endoplasmic reticulum. This is our classic example. And produce some proteins in the endoplasmic reticulum. Cytosis, we're going to go and produce some proteins in the endoplasmic reticulum. We're going to go and produce some proteins. It's really the reverse of endocytosis, larger molecule. Let's talk a little bit about exocytosis, which is how the cell is able to release larger molecules that might be used by the rest of the body, the other cells, or maybe it's going to be part of the extracellular matrix. And to understand how this works, it's really the reverse of endocytosis. We're going to go and produce some proteins in the endoplasmic reticulum. This is our classic example. Those proteins are then going to bud off in their own little vesicles, which then merge with the Golgi apparatus, where they are further processed. So they're processed in the Golgi apparatus right over here. And then eventually they're going to bud off of the Golgi apparatus in new vesicles. And those vesicles are going to make their way over to the cell's outer membrane, the plasma membrane, and the membranes of the vesicles are going to merge with the membrane of the cell, and in doing so, they're going to release their contents. And this is classic exocytosis. There are other cases where maybe it merges, partially releases the contents and then buds back. It's called the kiss and run method of exocytosis. But the classic one is it merges with the membrane. We can look at this membrane after the vesicles membrane has merged with the plasma membrane. The membrane might look like this. It might look like this. So if the vesicle, let me do the vesicles membrane in orange. The vesicles membrane is that in orange. Well, now it has merged like this, and it has released its contents. It has released the protein to be used someplace else in the body. And I want to be clear, this membrane, and I've talked about it many times in many other videos, even though I've drawn it as one line right over here, this is going to be a phospholipid bilayer. So if we were to zoom in, it would look like this. It's a phospholipid bilayer. So these are some of the phospholipids that were part of the original membrane. And then we also, in my little box, I get some of the ones that are part of, or that were part of the vesicle that was holding that protein. That were part of the, so these are some to zoom in. So a phospholipid, many times, someplace else, it has, the vesicle's membrane is that in orange. Well, now it has merged like this, and it has released its contents. It has released the protein to be used someplace else in the body. And I want to be clear, this membrane, and I've talked about it many times in many other videos, even though I've drawn it as one line right over here, this is going to be a phospholipid bilayer. So if we were to zoom in, it would look like this. It's a phospholipid bilayer. So these are some of the phospholipids that were part of the original, membrane. And then we also, in my little box, I get some of the ones that are part of, or that were part of the vesicle that was holding that protein. Was holding the protein. So I really want to really stress these lines that I'm drawing. These are bilayers of phospholipids. And all of these lines, these membranes that you see, these are all bilayers of phospholipids, just to make sure that we are visualizing this correct. And that's what exocytosis is. And one thing that I find interesting is when you first learn about it, you see a diagram like this, and you just assume, okay, well, these bubbles of these, these membranes, they just, randomly must float eventually to the membrane and where they get merged, and then they release their contents. But it actually isn't that chaotic. They actually can sit on tracks. So they actually can sit on tracks. Remember, we talk about the cytoskeleton, which isn't drawn enough, probably because it makes drawings really messy. But whenever we think about a cell, there's all the structure to it. Microtubules, microfilaments, intermediate filaments, all of these things over here that not only provide structure to the cell, but they can be used to transport. And these vesicles can actually ride on these structures. And you could actually have motor proteins that are using ATP to actively push the vesicle containing its contents. So this is
turning chemical energy into mechanical work. Muscle contraction, cell motility, vesicle movement.
It's kind of a transportation. It's really like a factory to push them towards the membrane so that they can be released. So whenever I think about it, it's fascinating because I always talk about these cells being a universe unto themselves. And they aren't just these blobs. They have all of these structures. There's all of these proteins that are really at an unbelievably small scale able to do these fairly intricate processes. So what I just showed you, once again, this is classic exocytosis. You'll see it when you have proteins, lipids being produced by the cell that need to be released somehow. They're also famously used in neurons when you want the chemical signal, when you go from one neuron to another, you have exocytosis of neurotransmitters that will trigger the next neuron. So these are very, very important processes. Our bodies would not function properly wouldn't function at all if we did not have exocytosis.
A bit too bright. Oh, interesting. Depends on the type of cell doing the phagocytizing. Yeah. Opsonin receptors. Opsonin receptors. Opsonin receptors. Opsonin receptors. Immunoglobulin G. AG. What the heck? Right. Right. A Sadducee. The pseudopods in? What is that? Pseudopods LN? What the heck? Vagiolysosome. Hmm. Oh. What the heck? Ooh. That's a good pop. Good pop.
I'm going to draw a little cell here for us. This cell is going to be a typical cell, and it's going to be full of potassium. We know that cells love to hold on to potassium. So let's draw lots of potassium in here. And the concentration of potassium, let's say, is something like 150 millimoles per liter. That's a lot of potassium, right? And I'm going to put brackets because brackets indicate concentration. And of course, there's some potassium on the outside too. Let's say the concentration here is something like 5 millimoles per liter. And I have to also show you how this concentration gradient gets set up, right? It's not like it just happens to be set up. It's something that we put a lot of energy into creating. So you get 2 potassiums pumped in, and you actually kick out 3 sodiums. So that's how you get all those potassiums in there in the first place. So now that they're in there, are they hanging out by themselves? The answer is definitely no. They are finding anions, little negatively charged molecules or atoms to sit next to. And so the net charge is going to be neutral, right? Because every cation has an anion. And usually these anions are things like proteins. Something that has maybe like a negative side chain, like a protein, could be a chloride, could be phosphate, could be a number of things. So any one of these anions would be fine. And actually, let me draw a couple of anions here as well for these 2 potassiums that just got welcomed into our cell. And so this is how things look. You know, if things are nice and static, this is how they look. And actually, to be quite honest, there's also a little anion hanging out here as well for this potassium. So now the truth is that we have little gaps in our cell, little holes where we allow potassium to actually leak out. So let's actually show how that would look and how that would affect what's going on. So we have these little channels, and they only allow potassium through. So these channels are actually very specific for potassium.
Sure.
They're not going to allow any anion through or any other thing out. The protein certainly can't get out. And so these potassiums are kind of looking at these channels that are there, and they're thinking, huh, this is interesting. There's a lot of potassium in here. We're going to want to just, slip out. And so these potassiums just kind of bail. So now the truth is that we have little gaps in our cell, little holes, where we allow potassium to actually leak out. So let's actually show how that would look and how that would affect what's going on. So we have these little channels, and they only allow potassium through. So these channels are actually very specific for potassium. They're not going to allow any anion through or any other thing out. The protein certainly can't get out.
Channels?
And
It's
so
a channel, right?
truth is that we have little gaps in our cell, little holes, where we allow potassium to actually leak out. So let's actually show how that would look and how that would affect what's going on. So we have these little channels, and they only allow potassium through. So these channels are actually very specific for potassium. They're not going to allow any anion through or any other thing out. The protein certainly can't get out. And so these potassiums are kind of looking at these channels that are there, and they're thinking, huh, this is interesting. There's a lot of potassium in here. We're going to want to just, slip out. And so these potassiums just kind of bail on the cell, and they just get right outside. Now, when they do that, an interesting thing happens. Most of them move outside, but there are some potassiums outside as well. I said that there was this one little fellow over here, and he could theoretically kind of make his way in over here. He could, come into this cell if he wanted to. But the truth is, overall, on the whole, on net, you have more movement outside than you do inside. And so I'll just, for the time being, erase that path. Just because I want you to remember that overall, we have more potassium that's going to move outside because of the concentration gradient. In fact, that's point number one. So actually, let me write that down here. Concentration gradient is going to make the potassium move outside. And that's on net. So the potassium starts moving out, right? So K out. And what happens next? Well, when it moves outside, let me actually draw it moving outside. So this K is now over here, and this K is over here. And what it's left behind is an anion. In fact, this guy's left behind an anion as well. And those anions, they are all by their lonesome, they start generating a negative charge. A big, big negative charge. Actually, just a few ions moving back and forth will create a negative charge. And these potassiums on the outside, they're thinking to themselves, huh, that's interesting. There's a negative charge in there. And if there's a negative charge in there, they're attracted to it because they're thinking, well, I'm positive. This is a negative charge. I want to go back inside. And so on the one hand, think about it, you have a concentration gradient driving potassium out. But on the other hand, you have this, what we call membrane potential, in this case, a negative one, a membrane potential that gets set up because the potassium is left behind an anion.
Sure.
That's actually going to drive the potassium to want to be back inside. So you have one force, the concentration driving K out, and another force, the membrane potential that gets created by its absence, that's going to drive it back in. So I'm going to actually make a little space here. I'm going to show you something that's kind of interesting. So let's create two curves. Let's say we have, actually, I don't want to lose everything on this slide. Let me actually just set this up here. You can see the last little bit of it. So let's set up two curves. One will be for the concentration gradient, and one will be for the membrane potential. So this is, let's say, K out. And you actually, if you followed it over time, this is time, you'd actually see that you actually have something like that. K is actually going to move out over time, and it's going to, at some point, get to an equilibrium. And if we did the exact same thing with time on this axis right here, and let's say this is membrane potential, and we start at time 0, and this is also negative axis, so this is going more and more negative this way. And we start at 0 for the membrane potential. And this is at the point where you start letting the K kind of wander out. You get something like this. Basically looks the same, but is kind of a parallel of what's going on with the concentration gradient. And when the two equal each other, when the amount of K moving out equals the amount of K moving in, we get to this kind of plateau. And it turns out it's about negative 92 millivolts. So that's the point where you really have almost no difference in terms of the net movement of K. It's equal. And in fact, we even call that term, we call that the equilibrium potential for potassium. So when you get to that negative 92, and it differs depending on the ion, but when you get to the negative 92 for potassium, you've hit its equilibrium potential. So let me just write that out. For K is negative 92. And again, this is assuming that the cell is only permeable to one thing, which is potassium. Now, this actually might still bring up a certain question you had. You might be thinking, and I want to make sure I address this, well, wait a second. If potassium ions are moving out, and that's what I said is happening, then at some point, don't we have a lower concentration in here because the potassium is actually left, and a higher concentration out here because, you know, potassium is moving outside? And technically, that is correct. I mean, of course, you have more potassium ions on the outside, and, you know, I haven't said the volume has changed, so yes, you'd have a higher concentration. And the same is true for the cell. You'd have a lower concentration, technically. But realistically, I haven't changed the numbers. And the reason I haven't changed the numbers is because if you look at the numbers, these are moles. I mean, this is a huge number, right? 6.02 times 10 to the 23rd. That's not a small number. And if you multiply it by 5, then you get something, you know, this kind of works out to about, I'm going to quickly do the math. 6 times 5 is about 30. And then you got millimoles here to consider. So about 10 to the 20 moles, right? I mean, that's an enormous number of potassium ions. And really, you just need a handful of ions to create this negative charge. So if only a handful of ions are moving back and forth, you're not going to really make a difference to that enormous number, 10 to the 20th. So that's why we don't really think of the concentrations as changing very much at all. It still bring up a certain questions are moving out, and that's what I said is happening. Then at some point, don't we have a lower concentration in here because the potassium is actually left, and a higher concentration out here because, you know, potassium is moving outside? And technically, that is correct. I mean, of course, you have more potassium ions on the outside, and, you know, I haven't said the volume has changed, so yes, you'd have a higher concentration. And the same is true for the cell. You'd have a lower concentration, technically. But realistically, I haven't changed the numbers. And the reason I haven't changed the numbers is because if you look at the numbers, these are moles. I mean, this is a huge number, right? 6.02 times 10 to the 23rd. That's not a small number. And if you multiply it by 5, then you get something, you know, this kind of works out to about, I'm going to quickly do the math. 6 times 5 is about 30. And then you got millimoles here to consider. So about 10 to the 20 moles, right? I mean, that's an enormous number of potassium ions. And really, you just need a handful of ions to create this negative charge. So if only a handful of ions are moving back and forth, you're not going to really make a difference to that enormous number, 10 to the 20th. So that's why we don't really think of the concentrations as changing very much at all. I'm going to draw enormous number of potassium ions. And really, you just need a So in the last video, we talked about how you have a higher concentration of potassium on the inside, around 150 millimoles per liter, than you do on the outside, let's say around 5 millimoles per liter. So, and just to recap some of the kind of important points we brought up, we said that essentially what happens is that you have these potassiums that are bound to little anions that are the green dots there. And because the concentration gradient is going to want to make the potassium leave the cell, it will. And so it'll leave the cell. Let's say this little fellow will leave the cell here, and he'll end up on the outside. So by doing that, he leaves that anion all by itself. And if this continues to happen, then these anions create this negative charge. And we can actually figure out exactly what that negative charge is. It turns out that that negative charge is going to attract back the potassium, right? We said that this potassium then is going to want to kind of swim back inside to be closer to that negative charge. And this is kind of that interesting idea, the idea that K leaves behind a negative charge and then it comes right back and wants to be by that negative charge. And the amount of negative charge that's going to offset the concentration gradient is around negative 92. So let me write that in now. So negative 90, that negative charge. And the amount of negative charge that's going to offset the concentration gradient is around negative 92. So let me write that in now. So negative 92 is the amount we know that we need to kind of offset the concentration gradient. So that's where we left off. And now I want to do a little thought experiment. Let's say that we come at this cell with a little injection full of, let's say, some positive charge. And try to ignore the kind of ridiculousness of what I'm saying just for the moment. But just focus on the positive charge. The fact that I'm going to pour a bunch of positive charge into this cell. And let's assume that we don't know exactly where this is coming from, but that this positive charge is essentially what it's going to do is it's going to make my cell not negative 92 anymore, right? It's going to make it more positive than it is. Let's say I make it, let's say halfway back to zero. So instead of negative 92, it's negative 46 millivolts. So this is the new membrane potential, right? And our cell is still just permeable to potassium, and that's really important. It's only permeable to one ion, that's potassium. So what's going to happen? Well, these potassiums, these little guys right here, they're going to notice that the charge is actually not right here. That's really important. It's only permeable to one ion, that's potassium. But this is the new membrane potential, right? And our cell is still just permeable to potassium, and that's really important. It's only permeable to one ion, that's potassium. So what's going to happen? Well, these potassiums, these little guys right here, they're going to notice that the charge is actually not drawing them back as strong as it was before. So this potassium might see that and it might leave. And so more potassium basically starts leaving the cell. And if more potassium is leaving and kind of going on the outside, then you have more of these little anions that are left behind, and the process continues, right? So these anions say, well, you know, if we're off by ourselves, we're going to contribute to this negative charge. We're going to add to it just as it did before. And that negative 46 is quickly going to go down again. It's going to slide back down. And the question is, how far does it slide down? Well, it goes back to the equilibrium point. So if we said negative 92 is what you need to make this yellow squiggly attraction, the membrane potential, equal the concentration gradient, if that's what's needed, then it will slide back down to negative 92. Goes back just as it did before. And that negative 46 is quickly going to go down again. It's going to slide back down. And the question is, how far does it slide? Anions that are left behind. And the process continues, right? So these anions say, well, you know, if we're off by ourselves, we're going to contribute to this negative charge. We're going to add to it just as it did before. And that negative 46 is quickly going to go down again. It's going to slide back down. And the question is, how far does it slide down? Well, it goes back to the equilibrium point. So if we said negative 92 is what you need to make this yellow squiggly attraction, the membrane potential, equal the concentration gradient, if that's what's needed, then it will slide back down to negative 92. So think about that for a second. It's pretty powerful stuff. I mean, you can do all sorts.
So we need to go above negative 92 millivolts for the potassium ions, for the potassium cations, right? Cat T plus cation, to then go back inside the cell and want to bind to those anions, right? Is that what I'm understanding?
Sorts of kind of funky things to the cell. You can add positive charge or negative charge. And as long as you maintain two important things, one of them being the concentration gradient. So one is this concentration gradient of 150 versus just 5. That's one thing. And the other is the permeability to only potassium. As long as you maintain the permeability, you'll get back to negative 92. So actually, let me even hammer this point harder by showing you a little diagram. So let's say we have a concentration gradient over here, and I also have permeability over here.
Does anybody know if my
and this is
logic
permeability
correct?
to potassium, okay? And assuming that we only have permeability, so assume, I'll write that very clearly, only the cell is only permeable to one ion, only one ion. So assume only one ion for this permeability. So if you have, let's say, permeability yes and permeability no, and you have concentration gradient yes and concentration gradient no, then what do you get exactly? So let's say you have 4 possibilities here, right? We have 4 possibilities. And let's say we have no concentration gradient and no permeability. Would we get a membrane potential? Well, no.
Definitely not, right?
Because the potassium would never have a way of leaving in the first place and would have no desire to leave. Now, what if you have concentration gradient, so you have the desire to leave, but you don't have a way for that potassium to actually leave the cell? Well, again, you don't actually have any membrane potential. And the same is true as if you have, a permeability, but you have no concentration gradient, then the potassium, again, has no desire to actually leave. And then finally, if you have permeability and a concentration gradient, then you actually get down to negative 92 millivolts.
Wow.
So concentration gradient is kind of when I use the word desire. Does the potassium... potassium have a desire to leave, and permeability is, does it have a means? Does it have a way to leave? So these are the 2 things to kind of think about when you're thinking about whether you would create a membrane potential or not. So if we have that set up, let's actually move down a little bit, make some space, and actually talk about how you actually get your negative 92. Where in the world does that number exactly come from? So there is a formula, and that formula is, I'm going to write it out over here. It's VM, and all that means is membrane potential. Now, if you're like me, the first thing you notice is that there's no V, there's no letter V in the word membrane or potential. So how do they come up with that? And I don't know the answer to that. I don't know where the V comes from exactly, but VM stands for membrane potential. And the formula is actually surprisingly simple. It's 61.5. And this is kind of a simplified version because there are a lot of constants in here that get kind of thrown together in that 61.5. And you just take the log of the concentration of potassium on the outside, I'll say K out, potassium on the outside, over the concentration of potassium on the inside of the cell. So you take these 2 concentrations and you get this fantastic little formula. And you can actually, now I can write for you potassium over here, we said was equal to negative 92 millivolts. So that would be the membrane potential. This is the membrane potential. And I can even walk through a few other ones, some other key ones. So there's sodium, there's, let's do chloride and calcium. So a few of them. And all of them have the same kind of formula. You just take their concentrations on the inside and outside and plug it into the formula, and you get positive 67 for sodium. You get negative 86 for chloride, and you get positive 123 for calcium. And now, keep in mind, calcium has a 2+ charge. So for calcium, this 61.5 actually gets changed to 30.75. And that's rounded off, but that's because of that 2 positive charge. And all you do is, as I said, throw in the concentrations on the inside and outside. So actually, let's even write that down. So concentration gradient, and keep in mind exactly which way things are moving. So concentration gradient for potassium, I mean, really you're looking at a positive ion, right? That's moving out of the cell. And for sodium, you have a positive ion, but it's moving into the cell. For chloride, you have a negative ion moving into the cell. And for calcium, you have a positive ion moving into the cell, really just like sodium. So this is how you kind of can think about the 4 major ions that contribute to our cell's membrane potentials.
Did I already watch it?
What if everything you did, thought, and felt could be communicated by pushing a button? It'd be like using the world's simplest app, one that just sends out a little ping, always the same volume and length, to communicate everything from "it sure is cold in here" to "I love churros" to "boy, I sure would like to breathe sometime soon." Well, that is actually exactly how your neurons send all the impulses responsible for every one of your actions, thoughts, and emotions. When a neuron is stimulated enough, it fires an electrical impulse that zips down its axon to its mirror neurons. So they've only got one signal that they can send, and it only transmits at one uniform strength and speed. What they can vary is the frequency or number of pulses. Like this is distinct from this. And your brain can translate these signals, reading them like binary code, organizing them by location, sensation, magnitude, and importance. So there's no difference between turn up the thermostat and oh my gosh, I'm a fire. That buzz, that nerve impulse is called the action potential. It's one of the most fundamental aspects of anatomy and physiology and really life in general. It's got it inside you right now, and we want to make sure that you understand what all that buzz is about. Before we delve into how neurons communicate, we've got to first understand a little bit of our old friend electricity. Basically, think your body is a sack of batteries. So I mean, you don't look like a sack of batteries. I'm just saying that your body as a whole is electrically neutral with equal amounts of positive and negative charges floating around, but certain areas are more positively or negatively charged than others. Because opposite charges attract, we need barriers or membranes to keep positive and negative charges separate until we're ready to use the energy that their attraction creates. In other words, we keep them separated to build potential. A battery just sitting on its own has both a positive and a negative end and the potential to release energy, but it doesn't do anything until it's hooked up to a flashlight or a phone or a kid's toy that lets those charges move toward each other on the way, converting electricity into light or sound or children's laughter. In much the same way, each neuron in your body is like its own little battery with its own separated charges. It just needs an event to trigger the action that brings those charges together. If you're thinking that this sounds more like engineering than anatomy, that might not be a bad thing. It might even help to think of your neurons in the same terms an electrician might use. Voltage, for example, is the measure of potential energy generated by separated charges. It's measured in volts, but in the case of your body, we use millivolts because it's pretty small amount. In a cell, we refer to this difference in charge as the membrane potential. The bigger the difference between the positive and negative areas, the higher the voltage and the larger the potential. And just like there's voltage in your body, there's also current, the flow of electricity from one point to another. The amount of charge in a current is related both to its voltage and its resistance. Resistance is just whatever's getting in the way of the current. Something with a high resistance is an insulator, like plastic, and something with a low resistance is a conductor, like metal. Now, when we talk about these concepts in terms of you, we're typically talking about how currents indicate the flow of positively or negatively charged ions across the resistance of your cell's membranes. And again, these membranes separate the charges, so they're what provide the potential to convert the electricity into something useful. Okay, now that we got electricity 101 down, let's see how it works inside your nervous system. A resting neuron is like a battery sitting in that sack that is you. When it's just sitting there, it's more negative on the inside of the cell relative to the extracellular space around it. The difference is known as the neuron's resting membrane potential, and it sits at around negative 70 millivolts. Where do those charges come from? Outside of a resting neuron, there's a bunch of positive sodium ions floating around, just lingering outside the membrane. Inside, the neuron holds potassium ions that are positive as well, but they're mingled with bigger negatively charged proteins. And since there are more sodium ions outside than there are potassium ions inside, the cell's interior has an overall negative charge. When a neuron has a negative membrane potential like this, it is said to be polarized. Now, these ions didn't just show up in this arrangement on their own. This is all orchestrated by one of the most important bits of machinery in your nervous system, the sodium-potassium pump. This little protein straddles the membrane of the neuron, and there are tons of them all along the axon. For every 2 potassium ions it pumps into the cell, it pumps out 3 sodium ions. This creates a difference in the concentration of sodium and potassium, and a difference in charges, making it more positive outside the neuron. This difference is an electrochemical gradient, and you probably know enough about biology by now to know that nature hates gradients. It wants to even out all of those inequalities in concentration and in charge to restore balance. But the only way to even out that gradient is for the ions to pass across the membrane. Thankfully, the sodium-potassium pump isn't the only way in or out of the cell. The membrane is also riddled with ion channels, large proteins that can provide safe passage across the membrane when their respective gates are open. And these gates open and close for different reasons depending on their structure and purpose. Most are voltage-gated channels, which open at certain membrane potentials and close at others. For example, sodium channels in your neurons like to open around negative 55 millivolts. So some others are ligand-gated channels. They only open up when a specific neurotransmitter like serotonin or a hormone matches onto it. Then we also have mechanically gated channels, which open in response to physically stretching the membrane. In any case, when the gates do open, ions quickly diffuse across that membrane down their electrochemical gradient, evening out the concentrations and running away from other positively charged ions. This movement of ions is the key to all electrical events in neurons, and thus is the force behind every single thing we think, do, and feel. Of course, not all of your body's electrical responses are the same, and neither are the flows of ions going in and out of your neurons. If only a few channels open and only a bit of sodium enters the cell, that causes just a little change in the membrane potential in a localized part of the cell. This is called a graded potential. But in order to send long-distance signals all the way along an axon, you need a bigger change, one big enough to trigger those voltage-gated channels. That is an action potential. And your best bet for making that happen is to depolarize that resting neuron. I mean, cause a big enough change in its membrane potential that it'll trigger the voltage-gated channels to open. It all starts with your neurons sitting there at resting state. All the ion channels are closed and the inner voltage is resting at negative 70 millivolts. And then something happens. Some environmental stimulus occurs, say like a spider brushes up against a tiny hair on your knee, triggering those sodium channels to open, increasing the charge inside the membrane. Now, the stimulus and the resulting change have to be strong enough to cross a threshold for the true action potential to kick in, and that threshold is about negative 55 millivolts. Remember that number, because this is an all or nothing phenomenon. If the stimulus is too weak and the change doesn't hit that level, it's like a false alarm. The neuron just returns to its resting state. So kind of like Doc Brown hitting 1.21 gigawatts in the DeLorean, once it hits that threshold, you're not going to travel in time, but you are going to see some serious action potential. At that threshold, the voltage-gated sodium channels open, and there are tons of these, so all of the positive sodium ions will rush in, making the cell massively depolarized. So much so that it actually goes positive, up to about positive 40 millivolts. This is action potential in action. It's really just a temporary reversal of the membrane potential, a brief depolarization caused by changes in currents. And unlike graded potentials, which are small and localized, an action potential kicks off a biological chain reaction which sends that electrical signal down the axon. Because each of your neurons has lots of voltage-gated sodium channels, so when a few in one area open, that local current is strong enough to change the voltage around them, and that triggers their neighbors, which triggers the voltage around them, so on down the line. As soon as all that's underway, the process of repol them, and that triggers their neighbors, which channels, so when a few in one area open, that local current is strong enough to change the voltage around them. That triggers their neighbors, which triggers the voltage around them, and so on down the line. As soon as all that's underway, the process of repolarization kicks in. This time, the voltage-gated potassium ion channels open up, letting those potassium ions flow out in an attempt to rebalance the charges. If anything, it goes too far at first, and the membrane briefly goes through hyperpolarization. Its voltage drops to negative 75 or so millivolts before all of the gates close and the sodium-potassium pumps take over and bring things back to their resting level. Now, when part of an axon is in the middle of all this and its ion channels are open, it can't respond to any other stimulus, no matter how strong. This is called the refractory period, and it's there to help prevent signals from traveling in both directions down the axon at once. So that is the surprisingly simple app that your nervous system uses to let you experience the world. And because the voltages in this process are always pretty much the same, the initial threshold around negative 55 millivolts and the peak depolarization at 40 millivolts, your neurons only communicate in a single monotone buzz. It doesn't matter if it's a spider on your knee or an elephant, a paper cut or a stab wound, the strength of that action potential is always the same. What does change is the frequency of the buzz. A weak stimulus tends to trigger less frequent action potentials, and that includes if the stimulus is coming from you, like your brain telling your muscles to perform some task. I mean, to do something delicate like pick up an egg, the signal is low frequency. But a more intense signal, like trying to crush a can, increases the frequency of those action potentials to tell your muscles to contract harder, and the message turns into something that you can't ignore. Action potentials also vary by speed or conduction velocity. They're fastest in pathways that govern things like reflexes, for example, but they're slower in places like your glands, guts, and blood vessels. And the factor that affects a neuron's transmission speed the most is whether there's a myelin sheath on its axon. Axons coated in insulating myelin conduct impulses faster than non-myelinated ones, partly because instead of just triggering one channel at a time in a chain reaction, a current can effectively leap from one gap in the myelin to the next. These little gaps are the delightfully named nodes of Ranvier, and this kind of propagation is known as saltatory conduction, from the Latin word for leaping. But what happens when an action potential hits the end of its axon and is ready to do more than leap and jump all the way to another neuron? That you will find out next time. Today, you learn how your body is kind of like a big bag.
Oh, these two are the same one. I think. Isn't boson actually the other guy? Gotcha. Okay.
So I've got 4 empty cells here. Let's imagine these are 4 cells in someone's body, and the inside of the cells are the same and the outside of the cells are the same. So they're really completely the same, except for one thing, and that one thing is that, let's say that these cells, each of them, is only permeable to one ion. And I'm going to write the ion that they're permeable to underneath them, right? So each of them can only let in or let out one ion. So in the first cell, you know that there's a lot of potassium that wants to get out, so it's going to have potassium leaving. In the second cell, you know that we generally have sodium, more sodium on the outside that wants to get in. And the same is true for chloride that wants to get in, and the same is true for calcium.
Oh, the same thing.
So this is kind of how the,
okay.
the 4...
Sorry, I'm just messing around. Okay,
so I've got 4 empty cells here. Let's imagine these are 4 cells in someone's body, and the inside of the cells are the same and the outside of the cells are the same. So they're really so I've got 4 empty cells here. Let's imagine these are 4 cells and
Dr. Rishi. Okay.
So I've got 4 empty cells here. Let's imagine these are 4 cells in someone's body, and the inside of the cells are the same and the outside of the cells are the same. So they're really completely the same, except for one thing, and that one thing is that, let's say that these cells, each of them, is only permeable to one ion. And I'm going to write the ion that they're permeable to underneath them, right? So each of them can only let in or let out one ion. So in the first cell, you know that there's a lot of potassium that wants to get out, so it's going to have potassium leaving. In the second cell, you know that we generally have sodium, more sodium on the outside that wants to get in. And the same is true for chloride that wants to get in, and the same is true for calcium that wants to get in. So this is kind of how the 4 cells are going to have movement of ions, and these are the concentration gradients. And so then, of course, if you want to figure out what the membrane potentials are, you have to think, okay, well, if it's a positive ion leaving, then it's going to make the membrane potential negative. In fact, we even calculated it to be negative 92 millivolts. Mm-hmm. And for sodium, it turns out to be positive 67 millivolts. And these are estimates based on rough concentrations. Of course, concentrations aren't exact everywhere, and different cell types have different concentrations. But these are kind of rough approximations. And chloride would be somewhere around, let's say, negative 86 millivolts. And you know it's negative because a negative ion is entering. And finally, calcium is going to be positive 123 millivolts. And just to remind us, the reason that calcium isn't simply sodium times 2, because you might think that, because calcium has 2 positive charges, the reason it's not just sodium's number times 2 is that these numbers are actually based on concentration gradients. And the concentration gradient for calcium might be very different. In fact, it is very different than it is for sodium. So that's how these numbers are made, using that Nernst equation that we went over previously. So now we know that these are the resting potentials for each individual ion. But what is the potential for a cell, a real cell? And we're not actually using a real cell as an example because, real cells are permeable to multiple ions. So let me actually give you an example of what a real cell might look like. Of course, it looks slightly different than that because you actually have potassium leaving, and at the same time, you might have sodium entering, you might have chloride entering, and you might have calcium entering. So this is what a real cell would look like. And let's figure out, maybe using an example, how to actually work through calculating the membrane potential for a real cell like that. So I'm going to write out the 4 ions and make it really clear so that we don't get confused about the 4. We're going to have, again, potassium, sodium, chloride, and calcium. And the reason I chose these four, I could have chosen others as well, but that these four probably contribute the majority to the resting potential. In particular, I would say potassium, but you'll see that all of them have a tiny little role in contributing to it. So let's first get to the idea of permeability. So until now, we've been assuming that each cell is, in the first example, only permeable to one ion. And now the whole difference is that now we have cells that have permeability to multiple ions. So here's how you think about it. Think about the fact that all ions crossing back and forth along the membrane make up permeability. Okay, so permeability is all ions crossing back and forth. Permeability is all ions crossing. I'll just write crossing, but you get the idea, crossing back and forth along the border. So what percentage is going to be from potassium? What percentage from sodium, chloride, and calcium? And of course, the total permeability has to be 100%, right? We have to add up to 100%. And let's assume right now that we only have 4 ions going back and forth. So I'm just going to make up some quick numbers. So let's say that of the 100%, potassium is 95%, meaning that 95% of all border crossings, if we think about our cell border, cell membrane, 95% of the crossings are with the ion potassium. And that means that only 5% of the crossings are with the other 3 ions. So let's say that it's 1% from sodium and 2% from chloride and 2% from calcium. So really, in terms of dominating the permeability, in this case, I've set it up so that potassium is dominating the permeability, right? And actually, in most cells, that's about right. Potassium is the dominant ion in most cells. In fact, sometimes even more than 95%. So how do you actually calculate the membrane potential based on this? So we've started with good information. We got the permeability, and now I need to multiply it by potassium's ideal membrane potential. What would potassium like it to be? It would like it to be negative 92 millivolts, right? And sodium would like it to be positive 67 millivolts. And chloride would like the membrane potential to be negative 86 millivolts. And calcium would like it to be positive 123. I mean, that's ideally where those ions would like to be. But again, 95% of the voting, in a sense, for what the cell is going to agree upon comes from one ion. It comes from potassium. And so we just have to add all of this up and get a total. So this part right here, 95% of the ions being permeable, multiplied by the membrane potential for potassium, 95% times negative 92. I'm just going to quickly do the math on a calculator. Works out to negative 87.4 millivolts. And this bit right here, 1% of 67, well, that's easy. That's 0.7 millivolts. That's just 1%. And then this bit, 2% times negative 86 millivolts, that works out to about negative 1.7 millivolts. And finally, this part right here for the calcium ends up being positive 2.5 millivolts. So if you add up all this stuff, what do you get? You get a total of negative 85.9 millivolts. So this would be the membrane potential for a cell that ended up having 95% permeability to potassium and only 1% and 2% to the other 3 ions. So if it's going to be dominated by potassium, you can see that this final number is going to be really close to what potassium would like it to be at negative 92, because 95% of it came from there. Now, that would be one way of doing it. Let me do it one more time, and you'll see how it can actually change. So just as before, let's say that in the second case, so again, this is case 1, this is case 1, and let's say case 2. Now I make potassium not very permeable at all. Let's say I drop it all the way down to 16%. Okay, 16%. And I raise sodium all the way up to 80%. So now all of a sudden, our same cell as before is very permeable to sodium. You might think, well, how would that be the case? Let's imagine that sodium channels get put into the cell membrane so that sodium can just go right through those channels. So something like that. But let's say that the other 2 ions stay about the same, 2% and 2%. So you've got a similar setup as before. And this time you've got, let me do the math. So we've got negative 92 millivolts. And again, the permeability, this is actually an important point, adds up to 100% again, right? Because you got 16 plus 80 plus 2 plus 2. So overall, we're still talking about 100% permeability. But in this case, most of that permeability is going to sodium. So negative 92 millivolts for the potassium. You've got positive 67 for the sodium, negative 86 over here. and you've got positive 123 over here. So I'm going to do the last two first because those are going to be the same as before, right? And we add them all up together. So here, of course, as before, I have negative 1.7. That doesn't change. And as before, I have positive 2.5. That doesn't change. So some of it's going to be the same, but some of it's going to be different. So these two numbers, let me just check out what my math works out to be. This is negative 14.7 millivolts. So a lot less than the negative 87. And now this is going to be a huge number, right? Compared to that measly 0.7 that we had before. Now we have 53.6 coming from sodium. So now sodium is playing a much bigger role than it was last time. And if I was to add up these four numbers, my overall permeability was 100%, and my overall membrane potential as a result of that is going to be 39.7. So it's positive 39.7. So we went from negative 85.9 to positive 39.7. And here, the dominant thing was this. So you can see how it's starting to approach positive 67, simply because we just had so much of the permeability coming from sodium. So in a way, the permeability becomes almost like a vote. Like the more permeable one of the ions is relative to the other ones, the more votes it gets in terms of what the final membrane potential is going to be. And in this case, the more an ion votes, the more it's going to be close. The final membrane potential will be close to what it wants, which is its resting potential. So we have these two membrane potentials. And finally, I'm just going to show you on a little graph what this might look like. So let's say you've got a little graph here. I'm going to draw positive and negative. So this is positive, this is negative, and this is millivolts. And what I'm drawing for you is the cell's membrane potential. The cell's membrane potential. Membrane potential in millivolts, right? So at time point 1, let's say time point 1 was right here, and time point 2 is right here. At time point 1, we had a very negative, I forget the number, I think it was like negative 80 something. I'll just say it was negative 86 or something down here. And then at time point 2, we had a number up here. This is our 39.7. And actually, let me just double check the number. I don't want to get it wrong here. Yep, negative 86. Okay. This is negative 86 or 85.9. So really, what you had is in just a matter of switching the permeabilities, you can actually change the membrane potential from something very low to something very high. So let's stop there and we'll pick up.
Something will pick up what? What are we picking up?
And we'll pick up. So I've got 4 empty cells here. Let's imagine these are 4. So we're going to talk about pace McWomb all the way to the point.
Is this where we pick up? Where do we pick up?
And we'll pick up.
Where do we pick up, buddy?
To be negative 86 millivolts. The ions is relative to the other ones, the more votes it gets in terms of what the final membrane potential is going to be. And in this case, the more these cells are going to work of stillicium into and out of a cell, it would be about 96 millivolts because it would be half and half what got there. We'll actually save myself some time by just now calcium pours in, and now the dominant ion in terms of the channels open. 1 parts, the numbers makers when they say that. That's called deep.
Okay, I don't know if we pick up, but okay. What do we pick up? That's it. It just ends there, huh? I don't know, but we got to keep moving. We got to keep moving. transporter? You want a transporter? Well, why? Why do you want a transporter, huh? I think we kind of went over it a little bit. I don't think there's any such thing as a protein channel. Okay, let's see. I think, okay, nephron reabsorbs glucose through a sodium glucose transporter. Sodium glucose. What is glucose? What sort of transporter is it? There you go, you already said it. Glucose. What sort of transporter? I think this was a there's a sync order. Maybe sodium pump. Maybe. I don't know what sort of transporter? He was a symporter. Oh, let's go. Boom, 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 boom. What's some property in the nephron? In the nephron, what type of cell was a nephron again? A kidney. It's a kidney cell. We're a nephron, nephrology, kidney. Nephron, nephrology, kidney. The kidney's capillaries allow small molecules to pass through. Emphatic. I'm not sure what that means. Fenestrations. Cholesterol RAS? What does that mean? This would make sense. I don't know. After what I learned, I guess not. Emphatic? What's emphatic? Emphatic. Fenestrations? What is that? Oh, small windows. Okay. Oh. Okay. I mean, sure. I don't even know. Slow. Which of the following would slow sugar equilibrium the most once the shutter is raised to connect the two solutions? So we want to slow sugar down. With slow sugar equilibrium down. I don't know. Tech. Looks like there's a lot of water here. There's a lot of sugar
Sorry,
here.
I didn't understand. But I found something related. Do you want to know, is it correct to say a lot of water?
No. No. Want to slow sugar equilibrium down. I think if we just increase the amount of water here now. It looks like there's some water and there's a little bit of sugar. There's some H2O here as well. Am I blind? Oh no, there's also H2O. Well, I don't know, I can't really tell, but now I just have, okay, there's a lot of sugar, some sugar, so would slow it down, would slow down the sugar going into the water, the other water, probably adding, I don't think adding is gonna make a difference. Adding salt, I don't know, maybe, possibly, I'm not sure. What do you think about that? Lowering the temperature? I don't think we talked about temperature. Lowering the water concentration inside A? Lower the water concentration? I don't think that's gonna make a difference, right? Lowering the water concentration. Lowering the water concentration. I feel like it might be D. I think that could slow it down. Slow sugar equilibrium down. Maybe D. Oh, never mind. The options was B? And then it's A. I guess it's A. What the heck? Oh, it was lower the temperature. What the heck? Is the size of the country. Second one. Equilibrium rate depends on kinetic energy. Depends on kinetic energy. Okay. Sure. Here takes place throughout the causes diarrhea, malaria, dehydration. Malaria. Check it. Dehydration. Effect of fluoride transporter. Fluoride transporter. Lead to dehydration. The toxin turns off transporter. I think Mars as a transporter with them. Secret current into the lunar. I think this makes sense. So in terms of Mars already exchanged. I'm thinking B. Oh, not the A. Maybe B. Cell membranes are water permeable. Constitutively turns on the transporter. Oh, the diarrhea. Forgot about diarrhea. Ah, gotcha. Okay. Okay. Potassium cyanide is in the sun. Okay, plus inside. Inside cell. It's ours. Up the membrane potential. Down the concentration gradient. Up the membrane potential. Isn't it down the membrane potential? They're moving up the membrane potential? I think it's A, isn't it? Oh, then it's B. Oh, what the heck? Potassium's trouble as I move into the cell? Oh. The inside of the cell is more negative. Oh, okay. Cells connected with ion X and placed in a solution with more potentials. With no net flow of X ions. Inside solution. There's no net flow of X. There's no way for them to channel and get outside. There's no probability for X. Transfer proteins? Cation. Jesus. X is a cation, so it remains in the cell. In order for memory potential to exist, the cell must be permeable, and there must be conjugated. It must be constantly charged on a cation higher in the cell. Okay. Selective serotonin reuptake inhibitors. Selective serotonin reuptake inhibitors. I think it's going to be the same problems. Secondary facilitate diffusion. Secondary active facilitate diffusion. I don't know if I wrote down. Okay. What sort of transporters would be required to move glucose from the blood to the lumen? From the blood to the lumen. Sodium glucose. Well, I think it's just the glucose you need. So I think you and usually it was a simpler, so I think we might be. Was that? C? Hmm. Damn, it's creating. Against the creating. Sodium concentration. Maintain sodium potassium concentration. Primary demotivated figures of manifestation. You could want to decrease the osmotic pressure, hydrostatic pressure. Maybe T. Okay. So use B. So that's the 4 different cells moving molecules across the plasma membrane. Which cells using which method of transport? C is using which channel? A. 3 to 2. I think D is using hydrogen, so I'm not going to C. D then? Oh damn, it was B. C is using hydrolysis? No, it's not that good. We're gonna have to go over it. Whatever, what can we do? Let's go ahead and move on to cell theory, which is what I would do. These. Up until cellular respiration is what I said, right?
Natural to just categorize a whole series of things as just being really, really unimaginably small. So when people say, hey, atomic scale or molecular scale or protein or a cell, you often just group that together and say, oh, those are really, 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 really small things. But what I want to do in this video is get an appreciation that even though all the things I just mentioned are really small,
All right, let's take it. Maybe it's like a 10-minute break. You know, we're gonna go through a lot. I mean, right now, I'm gonna go through it fast, but you know, there'll still be a lot technically. Cell membrane. Oh, these are some more videos. That's probably what I need, you know. Let's see if these explain a little better. I don't know. Let's see. But I'm not doing anything. Whoa, hold on, buddy. Yeah. Yeah, it's like a 10-minute break. Take a 10-minute break. Anki's gonna take us at least an hour and 30 minutes, so we have to remember that. And then the eukaryotic one is gonna be how long? So we did transporter cross cell, and we did cell. Eukaryotic will take us some time too, but it's just one article, so that's not too bad. Those rest are videos. I guess it depends how fast I can get these, you know, cell theory down, I guess. But I don't know. I'm just gonna keep going for a little bit up until we get to like maybe I do want to review this, so yeah, just up until intro to cellular respiration. I think that's okay. I think we can do it. I think we can do it. Whoa.
difference in the sizes of those things. And hopefully that'll give us an appreciation for how complex something like a cell can be, how it can have all of this machinery, how it can actually be a living organism or part of a living organism. And so at this scale, this is my little rendering, my drawing of a water molecule. You have the oxygen atom in the right over here in this purplish color, and then you have 2 hydrogen molecules bonded to it. And this is going to be roughly 0.275 nanometers. And just to remind ourselves, a nanometer is a billionth of a meter. And just to get ourselves an appreciation of that, so this is 1 billionth of a meter. That's a nanometer. If you want to even attempt to visualize that, that would be a millionth of a millimeter. So let me write this, 1 millionth of a millimeter. And I actually like using this one because a millimeter is about as small as I can on a reasonable basis visualize. But it's a millionth of that. So this goes well beyond at least my capabilities of visualization. So that would be the diameter or the width of a water molecule. Now let's go to the next scale up. We've talked a lot about proteins, and this is our friend, this right over here is our friend hemoglobin. And just to get a sense of scale, the width of hemoglobin is going to be about 5 nanometers, or 5 billionths of a meter. Now that seems super small, so in some ways it's okay to categorize that into your super small part of the brain, but to appreciate this is much larger than a water molecule. If a water molecule were on the scale, I pre-drew it, this little thing over here, that's my attempt at drawing a water molecule at this same scale. So even when you go from something like a water molecule to a protein, you're already going dramatically up in size and dramatically up in complexity. We've talked a lot about protein structure, they can take on all these interesting shapes and do fairly surprising and complex things inside of biological systems. But now let's go the next scale up. And the next scale up, I'm going to go to a virus. And what I've attempted to draw here, this is a fairly well-known virus. This is HIV. It's actually one of the larger viruses, and its diameter is roughly 120 nanometers. So if we were to draw this hemoglobin protein at the same scale as we've drawn this virus, this thing right over here would be the hemoglobin protein, and we wouldn't even be able to see the water molecule at this scale right over here. But this is still really, really small. This is 120 billionths of a meter. So this is still unimaginably small. But now let's go up to the next scale. So this creepy picture right over here, this is a T cell. This is a depiction. If you want to see the whole thing, that is a T cell right over here. This is a T cell. And this creepy picture, all the blue, that's a T cell. And what you see in yellow, that's the HIV virus emerging, taking advantage of this T cell. So that's why it's so creepy. It's using that cell's machinery to reproduce itself. But you immediately see on this picture how small the HIV virus is compared to the actual T cell. Each of these small things is an HIV virus, which we already saw is a lot bigger than something like a hemoglobin protein. And so hemoglobin protein, you wouldn't even be able to, on this scale, maybe it would be a pixel, if that. And on a similar scale as this T cell, you have things like red blood cells. This is actually a comparison, side by side. This is using electron microscope. You see a red blood cell right over here, and you see a T cell. They're roughly on the same size, or at least the same order of magnitude size. And a red blood cell is going to be 6 to 8 micrometers wide. So this is 6 to 8 millionths of a meter. Okay, so using electron microscope, you see a red blood cell right over here. You have the protein. You wouldn't even be able to, on this scale, maybe it would be a pixel, if that. And on a similar scale as this T cell, you have things like red blood cells. This is actually a comparison, side by side. This is using electron microscope. You see a red blood cell right over here, and you see a T cell. They're roughly on the same size, or at least the same order of magnitude size. And a red blood cell is going to be 6 to 8 micrometers wide. So this is 6 to 8 millionths of a meter. So if we were to just take 7 as the average, 7 millionths of a meter. Over here we're talking about a millionth of a millimeter. Now we're talking about 7 millionths of a meter. And just get an appreciation for size. We already compared the HIV virus, to this cell. We're seeing it directly as they emerge from the cell. But each of these red blood cells are going to contain roughly 280 million hemoglobin molecules. So they're going to be 200. Each of these is going to be 280 million of these. So 280 million hemoglobins in each one of these. So hopefully this starts to give you an appreciation for, even though we categorize cells as these unimaginably small things, they're actually far larger. They're ginormous compared to things even like large proteins, and especially when you think of things on the molecular or the atomic scale. And that's why cells are so interesting. They actually have a lot of complexity to them. But just have an appreciation also for how small cells are. Even though we've just described these red blood cells or these T cells as these kind of worlds unto themselves, they're these incredibly complex things. If I were to draw the width of a human hair on the screen right now, relative to the scale of these red blood cells, it would be about as wide as this video. So if I want to draw a human hair, it would go from there roughly to there. There's actually a lot of variance in the width of a human hair. But the width of a human hair would be just about like that. If you look at the scale of this picture right here, if you look at these scales, it would be much bigger. And I encourage you, we can think, okay, width of a human hair, pluck a hair out, look at it, put it on a piece of paper. It's hard to even discern the width. But we're saying that width compared to these red blood cells would actually be the entire width of the screen. We've already seen these red blood cells, these T cells, these are worlds unto themselves when you think of it from a viral or especially at a molecular scale.
It's like not balding. I can't get any hairs out. It's fine.
For granted the existence of cells, and the idea that all living, to us modern folk, we tend to take for granted the existence of cells, and the idea that all living things are made up of cells, and we, as human beings, as living organisms, we're made up of many cells. The estimates of the cells in the human body are on the order of 37 trillion cells. But if we were to rewind even 400 years ago to the 1600s, this wasn't so obvious. And that's because people really didn't have the tools to make direct observations of cells. They didn't know that these cells were around. They didn't know that things even like unicellular organisms even existed. But all that began to change with Robert Hooke. Robert Hooke was able to leverage primitive microscope, and this is a picture of his microscope. When you see this, you appreciate how, at least relative to what we have today, how primitive it was. He had lenses here that would provide some magnification, but he had to use this right over here. This is a flame, and he's able to channel that light so that it gets reflected over whatever he's observing. And in 1665, he publishes the Micrographia. I'm probably not pronouncing it right. So this is 1665. 1865, Robert Hooke publishes this, and in this he describes and he draws a lot of his observations using his microscope. And he has some fascinating drawings. He was actually quite a good artist, where he's able to draw pictures of his observations of things like lice and fleas. But it's not just lice and fleas that he's able to observe. He actually takes a look at some cork cell, or what he just sees as cork. And when he makes that observation, he says, "Hey, look, there are these little squares over here, and this kind of seems to be somehow kind of a basic unit of this cork." And he says, "Well, this kind of reminds me of these little rooms that monks live in and spend their time in, which we call cells." So he calls these cells, and that's where the word comes from. He calls them cells in micrographia. That is a cell. Now, unfortunately for us, he was a great artist, or he was really good at drawing things, and he drew a lot in his micrographia. But we don't have any pictures of Robert Hooke anymore. It's a fascinating story. Most theories are that actually it was Isaac Newton burned the only original painting that we have of Robert Hooke, and that's another intrigue.
Oh, really? Really? Oh.
Story that we can talk about at a future date. But when Robert Hooke, he coined these things cells, but he was looking at dead tissue, and actually he was looking at the remnants of cells, and what he saw was really just the cell wall remnants. He was looking at dead tissue, and actually he was looking at the story that we can talk about at a future date. But when Robert Hooke, he coined these things cells, but he was looking at dead tissue, and actually he was looking at the remnants of cells, and what he saw was really just the cell wall remnants. He wasn't actually able to observe directly living cells, and he didn't have enough to go on to think, hey, maybe this is a building block of all life, and maybe cells themselves reproduce, and all cells come from other cells. And that doesn't start to get developed until we get further on into history. You go a few years later, we get to Antony van Leeuwenhoek. I know I'm not probably pronouncing it right, but he was a Dutch lens crafter, and he was inspired by Hooke's work. He says, well, hey, I can craft lenses. Maybe I can use that to make better microscopes and make better observations. And he was able to do that. And doing that, he was able to directly observe living cells and living unicellular organisms. So he was able to directly observe sperm and say, wait, this thing looks like it's alive. He was able to directly observe protists. So these unicellular eukaryotic, they have cell walls, these things that look like unicellular animals. And he called them actually animalcules. Animalcules. Saying, hey, look, these look like these little mini animals going on here. And so he starts saying, well, maybe this is some form of a basis of life, or at least he's trying to say that these at this very small scale you actually have life. But a fully modern theory of the cell doesn't really start to emerge until we get another 100, 150 years into the future, and we get to the early 1800s. So if we fast forward to the 1830s, these two gentlemen, Matthias Schleiden and Theodor Schwann, come into the picture.
Matthias Schleiden and Theodor Schwann.
Sure. And they're the ones that start laying the foundation of what we could call modern cell theory. So modern cell theory, and using their observations and kind of what they were able to deduce, they said, hey, maybe all living things, all life, is composed of one or more cells. One or more cells. And today we kind of take this for granted, but this wasn't obvious. It wasn't obvious that all things, that this was somehow a building block for life, one or more cells. And then following that, if all life is composed of one or more cells, you could also say that a cell is the basic unit of life. Cell is basic unit of life. And these are strong statements that all life, if you were to get down small enough, you're going to come to cells, living cells that make up that life. Now, this isn't our full, complete cell theory, and both of these gentlemen, they knew that cells could come from other cells. They were able to observe cells reproducing, but it still was an open question. Hey, maybe some cells come from other cells, while others, maybe they somehow get spontaneously created if you have the right elements and the right amount of conditions. Maybe they somehow just emerge out of nothing. And it wasn't until this kind of third tenet of it wasn't until the mid-1800s that we get our third tenet of modern cell theory that gets established, and this is this idea that all cells come from other cells. All cells from other cells. And the real father of this idea, the one that really established this, is this gentleman right here, Robert Remak. Now, sometimes the credit for this goes to Rudolf Virchow right over here, but it turns out that he plagiarized Remak's work. Right over here. So it's really Remak who deserves the bulk of the credit for this tenet that all cells come from other cells. And once again, he wasn't the first person to say, hey, we'll observe that some cells come from other cells, but say, no, this is a fundamental thing. All cells, this is how they actually come about. They aren't just somehow spontaneously emerge. Now, whenever, even in today's world, people see this last thing, all cells come from other cells, there's a natural question, well, there must have been a first cell or an initial set of protocells, and people aren't 100% sure. But when we look back at the evolution of life on Earth, we think the first cells emerged about 3.5 billion years ago. And we're not 100% sure about how they emerged, but there are some theories. For example, we have videos on phospholipids, and it turns out that phospholipids naturally naturally form bilayers. So phospholipids naturally form bilayers, and they can actually form spherical. They can form spherical membranes that have phospholipid bilayers. So that kind of gets you a start. So that can spontaneously form. And there's also theories that maybe the information, the machinery of cells, maybe their ancestry for about 3.5 billion or longer ago, that it might have been, maybe it was self-replicating RNA molecules, or maybe it was somehow self-replicating proteins that over time, over very large time scales, were able to start replicating themselves, have more sophisticated machinery. The ones that had kind of were approaching our modern cells were able to reproduce more, were able to take advantage of kind of more of the energy, the resources in an environment, so that we eventually get with our modern cells. This is a fascinating question, and it's still an area of research.
Well, I think that's it. I think that's really all there is to cell theory, to be honest.
Hmm. Oh, I did this one.
Protists and things like that. And so if we, once again, just high level, we would consider these prokaryotes, and these, of course, are the eukaryotes. So hopefully that gives you a good overview of things over there. We call that the nucleolus. We call that the new nucleus over here. And then the other people, the current thought, it protein. So hopefully that overview of things.
I mean, we're gonna go through it. I think I might. Macromolecules. I want to go through this like another time. But for now, we're gonna have to skip it. I guess we'll just take it another time. I don't have the time. I think that might be it, to be honest, for cell theory. I don't know, there's not that much. It doesn't seem to be like there's a lot of stuff. It's not even on here, anyways. So let's just forget about it. And let's move on. Yeah, what article and the rest of videos. Save that page for something else. The strings in celery? Celery? Oh, okay. Sure. Ooh, there's a phone solo now. Oh. Ooh. It's lobster shells? Okay. You could just say we're making cracks. Just kidding. That's so small. What the heck? Perinuclear space. What's going on there? Huh? Like supposed to be graduation cap. That's funny. Oh wow, it's really going all over all of it, huh? All right, let's keep going. I mean, after this video, so it's not that bad. After this, we gotta read. Yeah. And then after we read, we gotta add. And then we gotta review the Anki. I've been looking at 12 tonight. It's continuous to the what? What? Oh, it's continuous to the nuclear core. What? Per nuclear attached to the nuclear envelope. What? Gotcha. It's time to with sugar. Also continues with the nuclear envelope. Become part of the membrane. Screen from the cell membrane out of the cell. What does the smooth portion do? Look at that. There you have a picture. We just skip what 2 is, but we know it's a nuclear core. 4, smooth is 11. Oh, 8 is the Golgi. 8 is the Golgi. 4 is the smooth. 4 is the smooth. To make lipids and steroids. Fats. Make fats and steroids. That would make sense. That would make sense. Golgi body, aka Golgi. Gotcha. Gotcha. Cytosol. I'm just a Cytosol kind of guy. Get out of here. Final destination. Lipid bilayers. Oh, there's 2 lipid bilayers. Sheesh. Inner and outer mitochondrial membranes. That's Manson's. Actin. Oh, these are really recent. These are, actually, I said this one 8 years ago. Okay. But I say these are really recent. Okay. Okay. Ah, so far. I wish I could go into night mode. Do I have night mode here? Do I have night mode here? How do I go into night mode? Oh, hold on, guys. Dark. 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 I don't think I can. That's okay. Just keep the glasses on, I guess. Oh, where were we? All right. Let's go ahead and watch the videos, and then add Anki, and then add the cards to the Anki, and that's it. And then we'll do the Anki.
In humans and all multicellular organisms, all living things are made of cells. In humans and all multicellular organisms are made of a type of cell called eukaryotic cells. But what is it that makes a cell eukaryotic? To answer that question, let's look at the two major types of cells. On the left is a prokaryotic cell. And on the right is a diagram of a eukaryotic cell. So let's define eukaryotic cells as different than prokaryotic cells. So usually eukaryotic cells are much larger than prokaryotes. And they're also eukaryotic cells are also found in multicellular organisms, although there are single-cellular eukaryotes, such as certain protists. But what are the defining characteristics that make a cell eukaryotic? The most important thing that eukaryotic cells possess that prokaryotes don't is the idea of compartmentalization. This is kind of a big word, but essentially what it means is that the cell is divided into different compartments. And we can see some of these compartments drawn here on the right in our eukaryotic cell, whereas our prokaryotic cell doesn't appear to have many different compartments. But why is it that the eukaryotic cell has lots of different compartments within it? Well, I kind of think of it as rooms in a house. So if you have lots of different rooms in a house, each room can do something different. So you could have a living room or in a kitchen and a dining room and bathroom and a bedroom, and they all have a different function. Prokaryotic cells then would be like a one-room house where everything is in a single room. And you see that this single room has to be able to do everything. So the compartmentalization of the eukaryotic cell into different compartments or kind of rooms allows each different compartment to have a different function. This is really important in the complex needs of the cells. The name for these compartments in the eukaryotic cell is organelles. Just like your body has different organs that have different functions, your heart pumps blood, your lungs take in oxygen, different organelles in the cell have different functions. These organelles are separated from other parts of the cell by membranes. And the name eukaryotic comes from one of these organelles. The word eu means well in Greek, and karyote means kernel or a nut. So when scientists originally looked at eukaryotic cells, they saw a very well-formed circular object in the center that looked kind of like a nut. And so they called these cells eukaryotes because they had a well-formed nut in the center of the cell. This nut is what we now know as the nucleus. The nucleus is a circular, membrane-bound organelle that contains all of the genetic material in the cell. So all of your chromosomes are inside the nucleus. This separates them from the outside of the cell. The nucleus is the defining organelle of eukaryotic cells. In contrast, prokaryotic cells have their genetic material, as well as everything else in the cell, just kind of floating around all in one big space. And so in prokaryotes, to divide and become new cells, all they have to do is make two copies of everything and then split down the middle in a process called binary fission. But in eukaryotes, we can see that because the cell has all of these different compartments or organelles, there's a more complex way to divide into a new cell. And the process that eukaryotic cells use to divide is called mitosis. So these are the defining characteristics of eukaryotic cells that sets them apart from prokaryotic cells. They're compartmentalized into different membrane-bound organelles, the most important of which is called the nucleus, which is responsible for the name eukaryotic. And finally, they divide by the process of mitosis. Let's go through some of the other important organelles within eukaryotic cells. So first, let's go back to the nucleus. And the nucleus I kind of think of as the control center of the cell, because that's where all of the DNA is and where DNA is transcribed into mRNA. Probably the next most important organelle in the body are called mitochondria. Mitochondria think of as the control center of the cell, because that's where all of the DNA is and where DNA is transcribed into mRNA. Probably the next most important organelle in the body are called mitochondria. Mitochondria you can think of as the cell's power plant, because the mitochondria is the site of cellular respiration where glucose is converted into ATP to provide the energy for everywhere else in the cell. The next organelle we'll get is called the endoplasmic reticulum. And so surrounding the nucleus are dozens and dozens of folds of membranes in this really complex pattern. But the unique thing about it, inside these folded membranes, is it's all continuous.
The lumen.
So it all encloses one single compartment, even though the membrane is folded back and forth on itself lots and lots of times. And the endoplasmic reticulum is primarily the site of protein synthesis. mRNA, which is transcribed from DNA in the nucleus, is translated at the endoplasmic reticulum. So I think of the endoplasmic reticulum as the factory of the cell, where proteins are produced. After these proteins are produced, they're sent to another organelle that also has kind of a folded membrane structure, but it's not a continuous compartment like the endoplasmic reticulum. And this organelle is called the Golgi apparatus. And the Golgi apparatus is kind of like the mailroom of the cell. So proteins that are produced in the endoplasmic reticulum are sent to the Golgi apparatus, and the Golgi apparatus is able to send those proteins to other parts of the cell depending on where that protein needs to go. So if the protein needs to be secreted by the cell, the Golgi apparatus sends it to the outer membrane of the cell and releases it. If it needs to go to a different organelle, the Golgi apparatus can send those proteins, as well as other biological macromolecules, to those sites as well. The last two organelles I'm going to mention are the lysosome and the peroxisome. And cells can have multiple ones of each of these, but I mention them together because they both have a similar structure. They're kind of a spherical organelle enclosed by a single plasma membrane. And the environment inside the lysosomes and the peroxisomes is very different from the environment outside in the cell's cytosol. So the lysosomes and peroxisomes are kind of like recycling centers in the cell. That's because when cellular components are no longer functional and need to be broken down, they're trafficked to the lysosome, where they are broken down into their more basic components that can be reused to rebuild new proteins or other macromolecules. The peroxisome has a similar function to the lysosome, but it's a little bit different because in the peroxisome is the site where reactive oxygen species like peroxides are reduced into non-toxic forms. So these are the main organelles of the eukaryotic cell. Remember, is defined by the compartmentalization of the cell into different membrane-bound organelles.
Thanks, buddy.
Here's a diagram of a eukaryotic cell. Let's look a little bit closer at the structure of one of the most important organelles in the eukaryotic cell, the nucleus.
Yes, sir. Yes, sir.
So here we have a depiction of the nucleus. Here's a diagram of a eukaryotic cell. Let's look a little bit closer at the structure of one of the most important organelles in the eukaryotic cell, the nucleus. So here we have a depiction of the nucleus. The most important function of the nucleus is to contain the genetic material of the cell. What is the structure?
Let's go back.
Here's a diagram of a eukaryotic cell. Let's look a little bit closer at the structure of one of the most important organelles in the eukaryotic cell, the nucleus.
Nucleolus.
So here we have a depiction of the nucleus. The most important function of the nucleus is to contain the genetic material of the cell. What is the structure?
DNA.
Sure. Let's look at the outside of the nucleus first. The nucleus is surrounded by two separate membranes, an outer membrane and an inner membrane.
Yeah. Nuclear envelope. An outer membrane and an inner membrane. Yeah. Four. It's right? It's got basically four. Am I thinking about that right? I think so.
Brain.
An outer membrane. Yeah. We've got two plasma membranes essentially, right?
Let's look at this structure up close. So we have an outer membrane.
There you go. That's what that's what I was thinking.
And we have an inner membrane.
And the inside is called perinuclear membrane.
These two membranes separate the nucleus from the cytoplasm, which is the liquid-filled space that makes up the majority of the cell and all of the non-compartmentalized
perinuclear space, I guess. Perinuclear space.
Parts of the cell. Essentially the parts of the cell that aren't enclosed within an organelle. On the inside of the nucleus is what's called the nucleoplasm. And the nucleoplasm is the fluid inside the nucleus. And so these two, into the cytoplasm and nucleoplasm, aren't continuous. However, a lot of the times stuff needs to be transported between the nucleoplasm and the cytoplasm. So think the interior of the nucleus is where mRNA is produced, but mRNA needs to get into the cytoplasm where it can be translated into protein.
All right, just get 10 minutes. I think I'm like classically conditioned now. I just have to take a break whenever that beeps. It's quite unfortunate. It's quite unfortunate. We'll finish this though. I will finish this. Add the cards, read it, even if I gotta stay up. Stay up because I have to get it. You know. I think I just messed around too much today. I guess. Whatever. Hey, Elusive. Hey, Jack. It's me. It's really me. It's me out here. Oh, message was retracted. What did they say before? How has studying been? Hope it's been good. Had a long day of studying too. Brain feels fried. Yeah. Yeah, I'm almost done, buddy. Yeah, I know what you mean, Jack. I know what you mean. Okay. I know what you mean. Yeah, I'm almost done. Probably another. I guess I'll be done at 12. I'm gonna see if I don't need to take the NyQuil for today. That's why I take it. I just can't wake up. So let's see what happens if I don't take it today, I guess. I'm gonna finish this. Then we gotta read. I read it before, I'll read it again. I don't care. And after we read, can I duplicate? I can duplicate. After we read, we have to I think it's just 84, huh? Nephron, exon, limitations. Yeah, I think it's just 84 for today. Yeah, I think that's all we covered. Basically. So we'll hit 84, and then we'll add the cards. We'll do Anki before we go to sleep. Actually, we should do a little bit of Anki right now, I guess. Oof. Mode proteins. Cytoskeletal fiber. Yeah, muscle contraction. Cell motility, vesicle movement. Dining. I forgot what they were called. Oh, myosin, kinesin, dining. Myo muscle, kinesin, dining. Sure. I think that's fine. Do I have to remember? Maybe. Hyperbolic. Oh no, this is a new one. Facilitate the fusion. Oh, doi. Okay. DNA replication. Feedback loop inhibition. Feedback loop. Yeah. Ligand protein channels. Ligand binder channels? Ligand gated. That's kind of close. Uncompetitive? Oh, let's go. I still got it. Coding suppressor proteins. Tumor suppressing proteins. That's okay. That's a little bit, I guess. I don't want to I want to do just some. You know, I just don't. I don't want it to be. I don't want it to be. I don't want it to be 12, and then it's like, you lost a streak, because I have a good streak going on. You know, what's my streak at right now? I don't know if you guys can see. It doesn't let you guys see from there, huh? But if I go in. If I go and see my current streak, which really should be more, but it's just I messed up that one day. Oh, well, you guys won't be able to see it anyways, huh? Anyways, I have a streak that I can see here on the Mac, but I can't see here on this one. I don't know why. But it doesn't pop up for some reason. You know, but at least it.
At least this shows here. And I like it. And I like it. You know, we're going strong. We're going pretty strong. So a lot of cards reviewed. At least, we reviewed some cards today. Obviously, I'm going to add some more cards, which I did last time. I didn't get to go over it. So we added those. I'll be going over those before the end of tonight. Well, actually, I'll be adding some more, and then we'll go over those as well. So I don't know how many cards we have today. Like, I don't know. Is it 60, 70, 30, 60, 70, 30, and then I might add, maybe I'll add another 50 or 100. But I think it only include, like, for today at least, I think like another 20. So it'll be like 200 something cards today. What was my stats last time? Like, what am I averaging? How many cards? No, the other one, it showed it on the Mac better. Showed it on the Mac a lot better. Whatever. Oh no, I'm not showing the wrong one. That's my ChatGPT, my little buddy, my little helper. There you go. Alright, I'll be back. We're back. I'm back, y'all. Oh. Hold on. We're not all the way back. Yes. I'm just gonna bring that exact same little bag when I go to drill this weekend. What are we at? We got an hour and 30 left for 12. And then I don't know. Hope I don't have to continue. We'll see. Just get it. Just get it. Get it. Finish up. Gotta get big. All right. Let's go. Let's do it. Wow, Doc, you're pretty big. Are you a bodybuilder? No. I just like to exercise. You know, you have to be. You know, you can't be a doctor if you're like. Well, you can, but just want to practice what I say, right? I mean, telling the patients, hey, don't. Or just tell me exercise and stuff like that. And like, well, you're not exercising. Well, you're not exercising. Don't worry about me. I'm just rambling. The ramblings of a madman. Somebody said that once, I think.
Protein. And also,
Let's get back. We're back.
proteins in the cytoplasm need to be able to get into the nucleus, such as polymerases, which convert DNA into messenger RNA. So this transport of things like mRNA out of the nucleus and protein into the nucleus happens at a special complex called a nuclear pore. And so there's another out of the nucleus inside.
Hold on, but just start from scratch. What are you talking about?
Here's a diagram of a eukaryotic cell. Let's look a little bit closer at the structure of one of the most important organelles in the eukaryotic cell, the nucleus. So here we have a depiction of the nucleus. The most important function of the nucleus is to contain the genetic material of the cell. What is the structure? Let's look at the outside of the nucleus first. The nucleus is surrounded by two separate membranes, an outer membrane and an inner membrane. Let's look at this structure up close. So we have an outer membrane and we have an inner membrane. These two membranes separate the nucleus from the cytoplasm, which is the liquid-filled space that makes up the majority of the cell and all of the non-compartmentalized parts of the cell, essentially the parts of the cell that aren't enclosed within an organelle. On the inside of the nucleus is what's called the nucleoplasm. And the nucleoplasm is the fluid inside the nucleus. And so these two, the cytoplasm and nucleoplasm, aren't continuous. However, a lot of the times stuff needs to be transported between the nucleoplasm and the cytoplasm. So think the interior of the nucleus is where mRNA is produced, but mRNA needs to get into the cytoplasm where it can be translated into protein. And also, proteins in the cytoplasm need to be able to get into the nucleus, such as polymerases, which convert DNA into messenger RNA. So this transport of things like mRNA out of the nucleus and protein into the nucleus happens at a special complex called a nuclear pore. And so there's a nuclear pore over here in my blown up diagram of the outer and inner membranes. What's interesting with the nuclear pore is that it spans both membranes, the outer membrane and the inner membrane, so that compounds in the cytoplasm can be transported into the nucleus and compounds in the nucleus can be transported out. But now the cell has gone to a lot of trouble to create these two lipid membranes to isolate the nucleus from the rest of the cell.
Right.
So the nuclear pore is actually very selective in what can be transported inside and out.
I would hope
And
so.
and the nuclear pore actually recognizes special signals on different proteins, and only with the presence of these signals can proteins be transported into and out of the nucleus.
Okay.
Through the nuclear pore.
Right.
So that the nucleus's primary function is to contain the cell's DNA or chromosomes. But when you look at the nucleus, is to contain the nucleus through the nuclear pore. So that the nucleus's primary function is to contain the cell's DNA or chromosomes. But when you look at the nucleus up close, you see there is a very densely compacted area. And this area is called the nucleolus. Just as the nucleus is kind of the center of the cell, the nucleolus is the center of the nucleus. But why is the nucleolus so much more compact and dense than the rest of the nucleus? Well, that's because the nucleolus has a very important function, and that is the site of ribosome assembly. So the nucleolus is densely packed with regions of DNA that produce not messenger RNA, but ribosomal RNA, which is the RNA that makes up the majority of the ribosome. And it is at the site of the nucleolus where this ribosomal RNA is assembled with the proteins that also make up the ribosome into a fully formed ribosome. And the ribosomes then can be trafficked through the nuclear pore out into the cytoplasm. The ribosomes also have proteins in them, and these proteins are produced in the cytoplasm and are trafficked back into, also have proteins in them, and these proteins are produced in the cytoplasm and are trafficked back into the nucleus where they can be assembled and then make the return trip back into the cytoplasm. So there's lots of stuff moving back and forth in the nuclear pores, but it's very important for the compartmentalization of the nucleus from the rest of the cell. To move into our next discussion, the nucleus is intimately associated with another organelle, the endoplasmic reticulum, which you can see in the faded green outline. An interesting topological feature of the nucleus is that the outer membrane, which we've drawn up in the top left, is actually continuous with the membranes that make up the endoplasmic reticulum. So I'll just kind of draw that. This outer membrane just turns around and actually becomes the membranes of the endoplasmic reticulum. And we'll draw it all in. So the interior space of the endoplasmic reticulum is continuous with the interior space between the outer and inner nuclear membranes. And one final term used to describe the nucleus is the nuclear envelope. And the nuclear envelope just refers to the combination of the inner and outer membranes along with the nuclear pores. So these three structures together comprise the nuclear envelope, which encloses the nucleus.
Thank you. Thank you, sir. Thank you kindly. 15 minutes on the mitochondria. All right, let's do it.
That are found in cells. Mitochondria are organelles that are found in cells, and they
it's Ephrat. It's Ephrat. She's pretty good. I like her.
are responsible for producing ATP, or adenosine. Mitochondria are organelles that are found in cells, and they are responsible for producing ATP, or adenosine triphosphate. ATP. Are organelles that are found in cells, and they are responsible for producing ATP, or adenosine triphosphate. ATP is a molecule that serves as the principal source of energy for cells, and for this reason, mitochondria are known as the powerhouse of the cell because they provide the
That's
cell
the
with
classic.
power.
Everyone's like, what is a mitochondria? The powerhouse of the cell. Yeah, well, what does it do? I don't know, but it's the powerhouse of the cell.
So here's a picture of a mitochondria that was kind of sliced down the middle. And let's take a look at its structure. So it has an outer membrane. And the outer membrane is made up of a lipid bilayer. And you might recognize that term as describing the cell membrane of a cell. And this lipid bilayer is not permeable to most things, but it is permeable to very small molecules. And that's because it has certain proteins embedded in it that allow small molecules to pass. The mitochondria also has an inner membrane, as you can see. And the inner membrane is also made up of a lipid bilayer, but it is not permeable to small molecules. And you'll see in a few moments why this is an important fact to keep in mind. And you may have noticed that the inner membrane is not smooth in the way that the outer membrane is, but rather it has many folds. And these folds are known as, well, individually each fold is a crista, in plural we call them cristae. And the reason that the inner
That's her name, Ephrat. Ephrat. It draws the cristae as white folds, but currently they're more like cavities connected to the perimeter of the inner membrane by narrow tubules called crystal junctions. Ooh.
Membrane is folded into these cristae is because on the inner membrane there are lots of different proteins that are necessary for cellular respiration, and by folding the membrane we just increase the surface area and allow a greater amount of membrane to be in a smaller space. So it basically just gives us more room to work with the enzymes and more room for cellular respiration to happen. And this space between N by T is because on the inner membrane there are lots of different proteins that are necessary for cellular respiration, and by folding the membrane we just increase the surface area and allow a greater amount of membrane to be in a smaller space. So it basically just gives us more room to work with the enzymes and more room for cellular respiration to happen. And this space between the outer and inner membrane is known as the intermembrane space. I'm going to write it over here on the side.
We gotta go a little bit faster.
And then the center of the mitochondria, we call that the matrix. So now that we've discussed the structure of mitochondria, let's see how that relates to cellular respiration and what happens here. Let's go through the steps of cellular respiration, which is the process by which we make ATP, and then let's see how it relates to the mitochondria. So the first step of cellular respiration is glycolysis. And what happens during glycolysis is the molecule glucose, which is a 6-carbon molecule, gets split into 2 molecules of pyruvate. Pyruvate is a 3-carbon molecule. And glycolysis actually does not happen in the mitochondria. It's the only step of cellular respiration that happens in the cytoplasm. Carbon molecule gets split into 2 molecules of pyruvate. Pyruvate is a 3-carbon molecule. And glycolysis actually does not happen in the mitochondria. It's the only step
happens in a cytosol
of cellular respiration that happens in the cytoplasm.
Okay.
The next step of cellular respiration is what's known as the PDC, or the pyruvate dehydrogenase complex.
Okay.
And what happens during the PDC is that pyruvate, and remember we have 2 of them, gets converted to a molecule known as acetyl-CoA. And you may recognize acetyl-CoA as the molecule that enters the Krebs cycle. And the PDC happens in the matrix of the mitochondria. So all the enzymes that are involved in the PDC are found in the matrix, of course, as well. The next step of cellular respiration is the Krebs cycle. And in the Krebs cycle, acetyl-CoA is going to undergo a series of reactions, which I'm not going to go into the details of that right now. And this happens also in the matrix of the mitochondria. And what I'm going to focus on right now is that at the end of the Krebs cycle, we produce 2 molecules, NADH and FADH2. And these are electron carriers.
Right.
You'll see in a moment why they're so important. And the last step of cellular respiration is the electron transport chain. The electron transport chain happens on the inner mitochondrial membrane.
Okay.
So on the membrane itself.
Right.
And this is the part where we're actually going to make ATP with the help of these electron carriers that we made during the Krebs cycle. So let's take a closer look at the inner mitochondrial membrane and see what happens during the electron transport.
Pyruvate dehydrogenase complex, pyruvate acetyl-CoA, Krebs cycle start with acetyl-CoA.
Transport chain.
Turns into what?
So look at the inner mitochondrial membrane and see what happens during the electron.
NADH and FADH2. Electron carriers. Electron transport chain.
Electron transport chain. So here's a more close-up diagram of the inner mitochondrial membrane. Let's just orient ourselves. Let's say that over here is the outer membrane, which would make this area over here the cytoplasm of the cell. And let's say that over here is the matrix of the mitochondria. And here, just label it as the inner membrane. So you can see the inner membrane is studded with a bunch of these enzymes, and these are the enzymes that are involved in the electron transport chain. And in case you want to know the names of these various enzymes, they're over here. Some of them are pretty long, so we're just going to refer to them by numbers. This one over here is going to be 1. That's NADH reductase. Then this white one, that's cytochrome Q. This green one is succinate dehydrogenase. Then we have number 3. I'm not going to mention the names. You can read them if you want. Then we have cytochrome C over here. And then there's number 4 right over here. So we have NADH and FADH2, which were produced during the Krebs cycle. And these are our electron carriers. And I'm going to describe what happens to NADH, but the same thing happens to FADH2. So NADH is going to be oxidized or lose electrons. So let's write out that reaction. NADH will turn into NAD plus, plus 2 hydrogen ions, plus 2 electrons. So it got reduced. And those 2 electrons, it got oxidized, it lost electrons. And those 2 electrons are going to go on to enzyme number 1. So while NADH lost electrons and got oxidized, the first enzyme gained electrons or it got reduced. But enzyme 1 is not going to hold on to the electrons, it's going to pass them on to the next enzyme, which is cytochrome Q. So now enzyme number 1 gets oxidized because it loses electrons, but enzyme cytochrome Q gets reduced because it gains electrons. And then the same thing will happen with the next enzyme. Cytochrome Q will pass those 2 electrons on to the next enzyme. And in case you're wondering where this enzyme 2 comes in, so FADH2, when it gets oxidized, its electrons go directly to enzyme 2, from there to cytochrome Q, from there to 3, etc. But anyways, back to what's happening with our NADH. So the 2 electrons are in enzyme 3, then they go to cytochrome C, then they go to enzyme 4, and then finally, those 2 electrons are used to reduce oxygen and make water. So I'm going to write 1/2 O2, which is the same as 1 oxygen atom, plus 2 H pluses, plus those 2 electrons give us water. 2 H pluses plus 2 electrons, that's the same thing as saying 2H. So we produce water. Let's go back to the electrons jumping from one enzyme to the next. When these electrons go from one enzyme to the next, they're going from a state of higher energy to a state of lower energy.
Right.
And when electrons go from a state of higher energy to a state of lower energy, they release energy. I'm just going to write energy kind of coming out of that, out of those arrows. And that energy is used for something. The enzymes in the inner mitochondrial membrane use that energy to do something. They use that energy to pump hydrogen ions out from the matrix and into the intermembrane space. If you recall, the intermembrane space is the space between the inner and outer mitochondrial membrane. So we're going to have, at the end of this process, a whole bunch of hydrogen ions in this intermembrane space. And that makes the intermembrane space more acidic. Sorry, not out there, right? The outer membrane, let's just, to make things clear. So we're talking about the intermembrane space. So the intermembrane space now becomes acidic, while the matrix becomes basic. And we know that in general, molecules like to go from areas of high concentration to areas of low concentration. And this intermembrane space has so many hydrogen ions, and they just want to get back into the matrix. But if you recall, we said that the inner membrane is not permeable even to the tiniest molecule. So the H plus ions cannot go through the inner membrane. There's only one thing that they can get back into the matrix, and that is they can go through this special enzyme known as ATP synthase. ATP synthase has special channels in it that will allow H plus ions to pass through. So the H plus ions will pass through these special channels in ATP synthase. And when they do, they're going to cause this axle to turn. Let's focus now on the bottom part of ATP synthase. It has this part of the protein has ADPs, adenosine diphosphates, and Ps or phosphates. There are a lot of them. I'm just going to draw one of each. And when the axle spins as the H plus ions go through, it's going to cause the ADPs and Ps to kind of knock into each other and attach. So ADP will attach to P, and we're finally going to produce ATP, the molecule that we're tracking through this entire time.
Let's go.
Let's just mention 2 terms that are relevant here. The first is chemiosmosis. Chemiosmosis refers to the hydrogen ions passing through the special channels in ATP synthase and then spinning the axle and making ATP. And another term you should know is oxidative phosphorylation.
Oxidative phosphorylation.
Oxidative phosphorylation, well, phosphorylation tells you something's being phosphorylated, so we're referring to ADP being phosphorylated, we're adding a P to it, and we're making ATP. And the term oxidative tells us that the phosphorylation is happening because of oxidation, because of the oxidation of NADH, and subsequently the oxidation of all these enzymes. Let's just recap everything that happened here. We had NADH and FADH2, which were produced during the Krebs cycle. They got oxidized, they lost electrons. Those electrons went on to the first enzyme, and from there on they went from enzyme to enzyme to enzyme. And when those electrons went from enzyme to enzyme, they went from a state of higher energy to a state of lower energy. When electrons do that, they release energy. That energy was used to pump hydrogen ions from the matrix into the intermembrane space. We have a bunch of these hydrogen ions in the intermembrane space. These hydrogen ions want to get back because there's a high concentration in the intermembrane space and low concentration in the matrix. But as we explained, the intermembrane is not permeable. When electrons do that, from enzyme to enzyme to enzyme, it got oxidized. They lost electrons. Those electrons went on to, and subsequently, the oxidation of all these enzymes.
Hold on, Efret.
ADP being phosphorylated, we're adding a P to it.
Talking too fast for me.
And the term oxidative tells us that the phosphorylation is happening because of oxidation, because of the oxidation of NADH, and subsequently the oxidation of all these enzymes. Let's just recap everything that happened here. we had NADH and FADH2, which were produced during the Krebs cycle.
Right.
They got oxidized. They lost electrons.
Right.
Those electrons went on to the first enzyme, and from there on, they went from enzyme to enzyme to enzyme. And when those electrons went from enzyme to enzyme, they went from a state of higher energy to a state of lower energy. When electrons do that, they release energy. That energy was used to pump hydrogen ions from the matrix into the intermembrane space.
From the matrix into the intermembrane space?
So we have a bunch of these hydrogen ions in the intermembrane space. These hydrogen ions want to get back because there's a high concentration in the intermembrane space and low concentration in the matrix. But
Right.
as we explained, the intermembrane is not permeable to H+ ions. So the only way for them to get back is to go through ATP synthase through the special channels in ATP synthase. When they go through, they spin the axle.
Cranks it like a cogwheel. Like a cogwheel? Or no, what? No, it's the water, like a water wheel. Is it called the water wheel? Water wheel. I think it's like a water wheel. Something like that. I think it's similar concept, I think. From what I remember a long time ago when I went over this.
That causes this part of the protein to knock ADP and P together, and that finally produces ATP. Is to go through ATP synthase through the special channels in ATP synthase. When they go through, they spin the axle. That causes this part of the protein to knock ADP and P together, and that finally produces ATP.
ATP.
And that ATP then provides the cell with the energy that it needs. There's one more topic about mitochondria that I'd like to discuss.
Okay.
And that is that mitochondria have their own genome.
Mm.
So they have one piece of circular DNA. It's a lot smaller than the amount of DNA.
Even since the mitochondria have one piece of circular DNA, they actually have multiple copies of their circular DNA chromosome. Also, mitochondrial DNA is found in the matrix.
It's found in the nucleus, but it allows them to do a lot of things on their own. Mitochondria are also self-replicating, so they can replicate independently of the cell in which they are. And because they have their own genome, they're able to make their own ribosomal RNA, tRNA, that's transfer RNA. They actually make some of the proteins involved in the electron transport chain. I'm just going to abbreviate that ETC. So ETC stands for electron transport chain. And they also produce parts of the protein ATP synthase. It's a rather complex protein, and they do produce some parts of it. However, most of the proteins in the mitochondria are actually encoded for by the nuclear genome. The mitochondria even uses a different system of transcription and translation.
What the heck?
And when I say different, I mean different than the nuclear genes. And mitochondria even has its own unique genetic code.
What?
So mitochondria are relatively independent organelles.
Sounds like it. The enzyme complexes harness energy. Oh, so it's the same.
Of the proteins of they can both H+ ions in the intermembrane space.
Which enzymes? So just other enzymes, I guess? Well, I guess I'll probably be in there somewhere again, I'm sure.
The endoplasmic reticulum is an organelle in the cell that buds off
This one's 9, this one's 5, and this one's so
There
10,
are 4
5
different
plus 7, 23 minutes.
that buds off of the nucleus. So let's say that this is the nucleus of a cell. The endoplasmic reticulum is an organelle in the cell that buds off of the nucleus. So let's say that this is the nucleus of a cell. It has a nuclear envelope, which is a double membrane structure. And this is the endoplasmic reticulum. Notice that the space in the nuclear envelope is contiguous with the lumen or space of the endoplasmic reticulum. So what does the endoplasmic reticulum do? Well, the endoplasmic reticulum actually has 2 parts to it. It has one part that's known as the rough endoplasmic reticulum. And that has a bunch of ribosomes. Those are the purple dots that you see. And then the endoplasmic reticulum has a smooth part. That part does not have any ribosomes. Let's start with the smooth endoplasmic reticulum first. So what does it do? The smooth endoplasmic reticulum synthesizes lipids, including those that will end up being part of the cell membrane, and those that are secreted from the cell. For example, steroid hormones. The smooth endoplasmic reticulum also metabolizes carbohydrates.
Lipids and steroids metabolize carbohydrates.
And it also aids in the detoxification of drugs and other toxins. Let's go to the rough endoplasmic reticulum. So the rough endoplasmic reticulum, as I mentioned, has ribosomes, which means it's the site of protein synthesis. But we know that there are also ribosomes that are in the cytoplasm. So what's the difference between those proteins that are translated in the cytoplasm and those that are translated in the rough endoplasmic reticulum? So let's split protein synthesis into 2. We have those that are made in the cytoplasm and those that are synthesized in the rough endoplasmic reticulum. So proteins that are synthesized in the cytoplasm will end up in a number of places. They might end up in the nucleus. They might end up in mitochondria, which I'm just going to abbreviate like that. They might end up in peroxisomes. Or they might just stay in the cytoplasm. Maybe that's where they belong. In contrast, proteins that are synthesized in the rough endoplasmic reticulum will either be secreted into the extracellular environment, or they will end up becoming integral proteins in the cell membrane, or they might remain in the endoplasmic reticulum, Golgi apparatus, or lysosomes. And you'll see in a few moments why I'm grouping these 3 organelles together. And I just want to mention as a side point that another thing that happens in the rough endoplasmic reticulum is post-translational modifications of proteins. For example, the formation of disulfide bridges in proteins, that happens in the rough endoplasmic reticulum.
Ooh.
Okay, let's go back to the protein synthesis that happens in the rough endoplasmic reticulum. So proteins that are secreted from the cell or that become part of the cell membrane follow what we call the secretory pathway. The secretory pathway describes the pathway a protein takes from when it's synthesized until it leaves the cell or becomes part of the cell membrane. But you might be thinking, how does a protein, quote unquote, know that it's supposed to be following the secretory pathway and therefore that it should be synthesized in the rough endoplasmic reticulum as opposed to the cytoplasm? So the answer to that question is that all proteins begin to be translated in the cytoplasm, but those that need to follow the secretory pathway have what's called a signal sequence. That signal sequence is detected early on in translation and will cause the polypeptide that's being synthesized to be pushed into the rough endoplasmic reticulum where translation is completed. In order for us to understand the secretory pathway, we need to talk about another organelle. That organelle is the
Golgi apparatus.
Golgi apparatus. The Golgi apparatus is an organelle that's found near the endoplasmic reticulum. And it's basically a group of sacs that are stacked together. And what happens in the Golgi apparatus? So the Golgi apparatus, the polypeptide is being synthesized to be pushed into the rough that are made in the rough endoplasmic reticulum. Number 2, the Golgi apparatus sorts and sends proteins to their proper destinations. And number 3, the Golgi apparatus synthesizes certain molecules that need to be secreted from the cell. Endoplasmic reticulum. And it's basically a group of sacs that are stacked together. And what happens in the Golgi apparatus? So the Golgi apparatus, number 1, modifies. And it's basically a group of sacs that are stacked together. And what happens in the Golgi apparatus? So the Golgi apparatus, number 1, modifies proteins that are made in the rough endoplasmic reticulum. Number 2, the Golgi apparatus sorts and sends proteins to their proper destinations. And number 3, the Golgi apparatus synthesizes certain molecules that need to be secreted from the cell. So let's take a look at a protein that was synthesized in the rough endoplasmic reticulum. Let's say that this part had a couple of ribosomes, and there was a protein made. Let's say this is the protein. So what will happen to it? So this protein has to end up either at the lysosome or outside of the cell or as a protein that's part of the cell membrane. So it'll butt off in a vesicle. Here's a vesicle butting off the endoplasmic reticulum. Of course, the protein is inside of it. And that vesicle will merge with the Golgi apparatus, and the protein will end up inside the Golgi apparatus. And this part of the Golgi apparatus is known as the cystostack. The cystostack is the part that's closest to the endoplasmic reticulum. Now this protein that's in the Golgi apparatus will undergo modifications. It'll get transferred to the middle part of the Golgi apparatus. The middle part is known as the medial stack. In the medial stack, it'll also be modified in different ways, and then it'll eventually land up in this part of the Golgi apparatus. This part is known as the trans stack. The trans stack is the part that's furthest away from the endoplasmic reticulum. And from the trans stack, a vesicle will kind of butt off, and that vesicle will be holding the protein in it. And from here, this protein can take a couple of different paths. One thing that might happen to it is maybe it's destined to land up in the lysosome. So let's say this is a lysosome. So in this case, the vesicle will move towards the lysosome, merge with it, and land up in the lysosome. I'm going to digress for just a moment. If you recall earlier, I grouped together the endoplasmic reticulum with the Golgi apparatus, with the lysosomes. And I'm going to add one more organelle to this group, the cell membrane. And the reason that I grouped all these organelles together is that they're all part of the secretory pathway. Take a look at the protein we just spoke about. It was made in the endoplasmic reticulum, where a vesicle butted off, then the protein landed up in the Golgi apparatus, and then another vesicle popped off, and the protein ended up in the lysosome. So all these organelles have ways of transferring proteins between them. Let's say the protein we mentioned was not supposed to go to the lysosome. Maybe it was supposed to go to be secreted from the cell, or maybe it's supposed to become a protein that's part of the cell membrane. So let's butt off another two vesicles. Let's say that this vesicle has in it proteins that need to be secreted from the cell. And let's say this vesicle has on its membrane a protein that needs to end up on the membrane of this cell. Let's see what happens to these two vesicles. So here's the vesicle with the proteins that need to be secreted, a protein that needs to end up. Here's the vesicle with the proteins that need to be secreted, and here's the vesicle with the protein that needs to end up in the cell membrane. So what will happen is the vesicle will move toward the cell membrane, merge with it, and release the protein. The same will happen with the other vesicle. It'll move towards the cell membrane, merge with it, and that protein will end up embedded in the membrane of the cell. And of course, at some point, these indentations will flatten out and the cell membrane will go back to its original shape.
Okay. Lovely.
Lysosomes are membrane-bound organelles. They're found in the cell. Lysosomes are membrane-bound organelles. They're found in the cell. What do they do? Well, if you look at the word lysosome, you can see the root lys, which means to cut or digest. So lysosomes digest various molecules and substances. And we can break this down into two different processes. The first is autophagy, and the second is chronophagy. Autophagy literally means self-eating. So autophagy is when the lysosomes digest molecules that are part of the cell itself or other cells. So for example, if there are organelles in the cell that are no longer functional, they will be digested by the lysosomes.
Dang.
So if there are some mitochondria or other organelles floating around that are old and not functioning properly, the lysosomes will break them down. Another example of autophagy would be the macrophages of the immune system. So macrophages of the immune system will engulf bacteria and viruses, and then they will go to the lysosomes and be broken down over there. Let's focus on chronophagy. Chronophagy is when the lysosomes digest excess secretory products. So let's say, for example, a certain cell is producing a hormone to be secreted, and the cell for some reason produces some extra. So let's say, for example, a certain cell is producing a hormone to be secreted, and the cell for some reason produces some extra of that hormone. All the extra hormones will be broken down by the lysosomes. And in both autophagy and chronophagy, after the lysosome finishes breaking down the molecules, it will release into the cytoplasm the building blocks that are just formed. It didn't exactly form those building blocks, but it broke the molecules down into their most basic parts, and those basic parts will be put into the cytoplasm and be reused. So for example, let's say the lysosomes digested some extra hormones that were lying around, and those hormones were made up of proteins. It'll break those proteins down into the individual amino acids, and then those amino acids will be released into the cytoplasm, and they'll be used for something else. What's the environment like in the lysosomes? Well, the enzymes in the lysosomes are known as acid hydrolases. And they're known as acid hydrolases because they require an acidic environment in order to work properly. So the pH inside a lysosome will be approximately 5. This acts as a safety mechanism for the cell. How so? Let's take a look at this lysosome right here on bottom. Let's say for some reason it burst and released into the cytoplasm all these acid hydrolases that we just learned are capable of digesting organelles. Well, we said that in order for them to work properly, they need to be in an acidic environment. But the cytoplasm has a pH of approximately 7.4. And therefore, these acid hydrolases are not going to function properly. You might say, well, when the lysosome bursts, doesn't it release some acid into the cytoplasm? And that's true. However, it's still going to be a pretty small amount, and it'll get diluted in the cytosol, and the cytoplasm will still remain overall at a pH of about 7.4. However, if many lysosomes burst at the same time, it would release a larger amount of acid into the cytoplasm, and then the cytoplasm might actually become more acidic, and the acid hydrolases will start to work and will start to digest the various organelles. And this, generally speaking, would not be a good thing for the cell.
Right.
Let's talk about another membrane-bound organelle that's pretty similar to lysosomes, and they're known as peroxisomes. Peroxisomes are responsible for a variety of metabolic activities. In some cells, they're essential for lipid breakdown. They help liver cells detoxify chemicals and drugs, but we're going to focus on one important task that they carry out. So let's zoom in on one peroxisome. Here it is. So what do? Well, there are various enzymes in the cell that, as a result of their activity, they produce a byproduct, hydrogen peroxide, which looks like this. Hydrogen peroxide happens to be pretty dangerous for the cells. What peroxisomes will do is they're going to isolate it, so the hydrogen peroxide ends up in the peroxisome, and each peroxisome has an enzyme known as catalase. And this enzyme is able to break down hydrogen peroxide. So let's write out the reaction. Hydrogen peroxide, in the presence of the enzyme catalase, will become water and oxygen. I'm just going to put a half there to keep the ratio correct. So peroxisomes protect the cell from the damaging effects of hydrogen peroxide by isolating it and by then breaking it down into water and oxygen. And each peroxisome will become water and oxygen. I'm just going to put a half there to keep the ratio correct. So peroxisomes protect the cell from the damaging effects of hydrogen peroxide by isolating it and by then breaking it down into water and oxygen. Different types of animal tissue. There are 4 different types of animal tissue that are all made up of eukaryotic cells: epithelial tissue, connective tissue, muscle tissue, and nervous tissue. In this video, we're going to talk about epithelial tissue and connective tissue. So when you think about epithelial tissue, you can think about it as a lining, both an inner lining and an outer lining. So for example, epithelial tissue makes up the outer layer of our skin. It makes up the outer layer of organs. It lines organs, so the lumen of organs will be lined with epithelial tissue. And it also lines the inside of the cavities of the organism. Epithelial tissue also make up glands, so that would include both exocrine glands and endocrine glands. And just to remind you, exocrine glands will release their substances directly to the target organ, whereas endocrine glands usually release hormones, but into the bloodstream, not to the target organ directly. And endocrine glands. And just to remind you, exocrine glands will release their substances directly to the target organ, whereas endocrine glands usually release hormones, but into the bloodstream, not to the target organ directly. And epithelial tissue comes in 2 forms. It can be simple, and that means it's 1 layer thick, or it can be stratified, which means it can have 2 or more layers. And where would you expect to find simple epithelium versus stratified epithelium? Well, you'll find simple epithelium in places where substances need to diffuse from 2 different places. So for example, the alveoli of the lungs are lined with simple epithelium because carbon dioxide and oxygen need to diffuse from the alveoli. You'll find simple epithelium in places where substances need to diffuse from 2 different places. So for example, the alveoli of the lungs are lined with simple epithelium because carbon dioxide and oxygen need to diffuse from the alveoli into the bloodstream and vice versa. And of course, that would be pretty difficult if you had a thick layer of cells. And you'd expect to find stratified epithelium in places that need to resist chemical or mechanical stress. So for example, the esophagus is lined with stratified epithelium. That's because the esophagus will have food coming through it. The food might be sharp, it might be hot, and we want a thick layer of cells to protect the underlying tissue of the esophagus. So a stratified layer of epithelium acts as that protective layer. Let's take a look at a section of simple epithelium, and epithelial cells are attached to something known as the basement membrane. The basement membrane is not made up of cells, but rather it's made up of different types of fibers. For example, one fiber that can be found in the basement membrane is collagen. And the basement membrane is semi-permeable to certain substances, and that's pretty important because epithelial tissue is avascular. That means that epithelial cells have no blood vessels, which then makes us ask the question of how do they get nutrients? So they get nutrients from the underlying tissue. So what happens is that nutrients will diffuse from the underlying tissue through the basement membrane to the epithelial cells.
Hold on.
So they get nutrients from the underlying tissue, certain substances, and that's pretty important because epithelial tissue is avascular. that means that epithelial cells have no blood vessels,
These are the epithelial cells here. They got no blood vessels.
which then makes us ask the question of how do they get nutrients? So they get nutrients from the underlying tissue.
The underlying.
So what happens is that nutrients will diffuse from the underlying tissue through the
Through the basement membrane?
basement membrane to the epithelial
Ooh, gotcha.
cells.
Gotcha.
And that's how epithelial cells get their nutrients.
Okay.
Let's just recap some of the places that you'd expect to find epithelial cells. So we already mentioned the outer layer of the skin, the tissue lining the mouth, esophagus, and GI tract. And
Okay.
of course, this is not an exhaustive list.
Right.
In the tissue lining the kidney tubules,
Kidney tubules.
and the tissue lining blood and lymphatic vessels. And in fact, the tissue that lines blood vessels and lymphatic vessels has a special name. It's known as endothelium. Let's talk about connective tissue. So connective tissue supports tissues, lymphatic vessels has a special supports tissues, connects tissues, and separates different types of tissues from each other. And so connective tissue supports tissues, connects tissues, and separates different types of tissues from each other. And then there are different types of connective tissue that don't necessarily fall into these neat categories. So what are some examples of connective tissue? Bones, cartilage, blood, lymph, adipose tissue, which is fat, the membranes covering the brain and the spinal cord, and other types of tissues. So what does connective tissue look like? What are some characteristics of connective tissue? So basically it has three components. It has cells, it has what's known as a ground substance, and then it has fibers. And the ground substance and the fibers together make up a matrix. So let's see what this looks like. Here we have the ground substance, which is usually a viscous type of fluid. Then interspersed in the ground substance are fibers, and then we have cells. And these cells are usually what's producing the matrix. Let's look at some connective tissue in more detail. So the first we'll talk about is areolar tissue, which is this tissue right over here. So areolar tissue is a very common type of connective tissue. It binds together different types of tissue and it provides flexibility and cushioning. And we can actually see the structure pretty clearly in this picture. You can see the cells over there, those little dots. There's another cell over here. You can see the fibers running through it over here and over here. And then the ground substance is the kind of background yellow viscous liquid that you're seeing. Then we have adipose tissue. Adipose tissue is basically fat, tissues of fat. It provides cushioning for the body, it stores energy, and it actually is an exception to the rule. It does not have fibers like most other connective tissue. Then we have what's called fibrous connective tissue. Fibrous connective tissue is pretty strong. It provides support and shock absorption for bones and organs, and you find it in the dermis, which is the middle layer of the skin, tendons, and ligaments. Here are some more types of connective tissue. We have blood. So blood is also an exception like adipose tissue in that it does not contain fibers, and the matrix of blood is the plasma. You can see the matrix, this yellowish liquid in which the blood cells are suspended. Then we have osseous tissue or bone tissue. These cells in osseous tissue are known as osteocytes. Those are those brown cells that are kind of forming a pattern. And the matrix in osseous tissue is what's known as bone mineral or hydroxyapatite, which is basically collagen fibers with different minerals like phosphates, magnesium, calcium, etc. And then we have hyaline cartilage. The cells in hyaline cartilage are chondrocytes. You can see them over here. There are a bunch of these cells, and they're found in surfaces of joints. So these are all examples of different types of connective tissue, and many of them provide some form or another of support for tissues and organs.
Okay. Okay. Let's I think let's just read this one again now. I think we should add the cards. I can always read this tomorrow. I don't want to be what I don't want to add the cards tomorrow while I focus on watching the other videos. Let's just add the cards. What would I mean? Let's type in cell-cell interactions. That's under the deck. Oh, miles down. No, which one was it? Huh? What the heck? No, I mean, we just had it. Are you serious? Are you serious? Oh, high yield Anki. It's actually high yield Anki. I should be looking at. Just has high yield Anki. Let's take a look at the high yield Anki. High yield Anki. Dum, 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 dum. No, it's not. What the heck? Kind of want to. I feel like adding all of this, but I'm not really there yet. Formation of the germ cells. Maybe, I mean, I think this stuff I can probably add. And then homologous chromosomes. This maybe I can add. This I can probably add. Central dogma. Got that dogma in them. DNA mutations were added. Enzyme kinetics and Manton saturation curve. Exon and introns. Kinematics. No, physics. Les Chateliers we added. Mendelian genetics we added. Organelles and all things plasma transport. Organelles and all things plasma transport. Yup. 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 Get them all in there. Protein structure, nuclear molecular forces, reduction and oxidation. I don't think I'm there yet. Sure. That's high yield. What's in this one? I don't know, like, why this one doesn't have. This should have been on there. This is pretty good. Troponin, I don't think I'm on there yet. T helper cells, short-term memory, secondary structure. No. Relax state. No. Oh, reduction? Maybe. What is this? Oh, secondary active transport. It's pretty good. This one is pretty good. Sure, I like that one too. This should have been in there. What the heck? What the heck? I'm not in this one yet. Oxidative phosphorylation. That one, I guess I could have. I mean, it's coming up. I might as well. Operant conditioning. Nope, nope, and nope. And I'm not on glycolysis or anything there yet. I can add this stuff, I guess. Glycolysis. No. Cell-mediated immunity, active transport. We can add all this though. Contractin, myosin heads, actin. I think this one, maybe, right? Actin. Oh, I think maybe this one. Maybe. Quite possibly. Quite possibly, yes. I don't think we're really at the action potential stuff yet. I mean, yeah, this is all stuff that should have been there, though, for sure. What the heck? It says bioenergetic stuff. Chaos Benton. It should have been in there. This should be in there, too. I don't know about that one. I feel like maybe. But I don't know. Isoelectric point. Kinetics. It should be in there. It should be in there. Central nervous system. I'm not sure. Troponin? I'm not sure about this one. Okay, ETC. I don't think I'm here yet. This stuff should have been in here a long time ago. This stuff should have been in there a long time ago. Krebs cycle. Operant conditioning. I'm not sure. I think that's some psychology stuff. This should be in there. Be in there. Should be in there. Should be in there. Peroxisome should be here. Peak reaction. Passive transport. This one we can add it a little bit now, I guess. This should be here. Mitochondria. Lysosome should be here. Pressure leaves. That should be in there. Should be in there. This should be here too. What the heck? Jesus, it's so hot. I don't know if like these are being added, like as they're adding it, or if these are just something I completely forgot. Like these are some that I completely forgot to add. No, because I'm always seeing some of these and like, what the heck? I added you guys here. How are you like? Maybe this stuff. And this rest, I don't know what these are. I think these are just like extras. I don't know. I think it's probably I should do some of these to be honest. These are like just keeps me on my toes, you know. I guess. What does that say? I can't tell. This one, maybe I should add this one too. Okay. Alrighty then. And then now let's check the decks, just the whole thing, I guess, and see. Now just do it by. Stop it. Cell junctions. Yep. I don't know if I really need to know all of this though. See, this one was on there. And I was like, what the heck? From where? From where? Let's see if this is something we've gone over. Possibly. Excuse me. Cell-to-cell junctions. I mean, I guess this wasn't even part of it. Something I've seen. Okay. Honestly, I might just yeah, whatever. I just add them all, dude. Like, who cares? Command AJ. They all seem to be fine. Cell-to-cell junctions. Cell-cell junctions. The cell junctions. No. Membrane receptors. Huh? Did we do this one? No, that's immune system less than 10. We're nowhere here. We're nowhere near here, so I'm not gonna do that one. Get out of here. Let's be a little bit more picky with this one. G protein. Yeah, we'll do G protein. G protein, GPCRs, all GPCRs. Extracellular ligands, yeah. G proteins, we'll do G proteins. Complement on this stuff? No. G proteins, we'll do G proteins. Sure. Meta. Quiet down. Ion. Ligand gated ion channel. What time is it? I gotta restart the stream. No, yeah. Yeah, banana in the crap. GPCRs. GPCR. There's a lot on this one, huh? What about this one? What's the link to this one? How cells signal relay pathways. Really? We gotta get in there with that one. Wow. Okay. Now the archive. You mean that? Where is this one at? Oh, how cells communication? How cells signal to each other? Gotcha. I gotcha. I don't know. Maybe. I think I might. I don't know. That's kind of a lot. This is a high yield right here, though. Adrenergic. The steps in olfaction. No. Rhodopsin. No. GPCR sequence. Maybe. Yeah, probably. Yeah. All right. GPCR. And that's all of it. Enzyme ligated. enzyme linked receptor. Biosignaling. Nice. Cell theory. The sliding filament theory. I don't think that's anything. Okay. Transport. Transport across cell membrane. Yeah, everything here. Nice. Passive transport. So there's a little bit some osmosis. Get in there. Part of the nephron. I don't think so. What the heck? Preview? Where did we go over this? I think that's like way later probably. No, I'm okay. No, thank you. Facilitated diffusion. I don't think I spelled it right. Facilitated diffusion. Oh my goodness, I'm blue this one out. Facilitated diffusion. Facilitated fusion. See, I almost missed 3 cards. Would you look at that? They're trying to get me. Diffusion. I gave 3 ways the signal in the synapse can be terminated. I don't know. Maybe we might get here, so I'll just add it, I guess. Fusion from synapse. When are we getting here, actually? Oh, actually, we're not getting here for a while. We're not getting here till week 3. What the heck? Get back outside. Become suspended. What are you trying to do? Oh, I think I might have done some synapse stuff. I guess I'll take that out. Well, I'll take it out later. Osmosis. Nice. Oh, thank you. Exocytosis. Endocytosis. Pinocytosis. Yeah. Phagocytosis. Where is this one at? This might be viruses, which I think we'll do week 2. Let's check it out. Immunology. I don't think I'm here yet. Immune system is end of week 3. So maybe not. No, thank you. No, thank you. Phagocytosis. Okay, we're good. Membrane proteins. Membrane proteins. I know that's not the way later. Oxidation and phosphorylation. Electro-oxidative phosphorylation. That's PAMCAL. Well, thank you. Permeability. Yeah. Basically, oh no, not this stuff. Fluid mosaic model. And that's nephro stuff. I don't think I'm hearing you. Okay. Cellular organelles. I think I misspelled it, huh? All of them. Organelles. I think it's 2 L's. Where was this, by the way? That's Unit 7. What the heck? We're not even there yet. Oh, but we'll be by the end of tomorrow, so I might as well just add it today. How about just if I type in organelles? Not really, huh? I don't know. What's this red blood cell one? Is that part of it? It's not even there, really. What the heck? No. I'm good. I think she did go over this one though. Yeah. This one we will add. Definitely add you. Definitely add you as well. Yeah, you seem pretty good. You seem good too. You also get epithelial cells too. What is considered, I think maybe, let's see. Do we add you? Yeah, we add you as well. I'm guessing we just add everything here, huh? Sure. Eukaryotic cell. Citric acid cycle? I guess I do too. Nucleus. Not just nucleus, cell nucleus. No. Nope. Mitochondria. Urea, NADH. Mitochondria. Maybe just add the basic layers here, I guess. I don't know if I want to sort this yet. That's not like a bunch of stuff. I don't know. I don't think so. Just wait there. Just wait till we get there. Endoplasmic reticulum. We're good. Golgi. Seems pretty good. Seems pretty good. Lysosome. Seems good. Lysosomes. Peroxisome. Oxidative reactions. What are we getting there? Oxidative reactions. Are we doing that? So maybe not. Huh? Huh? Biosignaling. Oh, maybe like more of the pathways. Yeah, right here, oxidative phosphorylation. Maybe. Cellular respiration. I don't know. Reduction and oxidation reactions. No, I don't think so. I think that's for later. Oxidative phosphorylation. That's somewhere here. I don't think I'll add it to that till then. Epithelial. Epithelial. And collective tissue. epithelial. How about epithelial tissue? That's behavioral. Connective tissue. No, I don't know. I don't think so. I don't know. Is that part of it? Is that part of today's thing? No, no. That's some other stuff. Alright, I think that might have been it. Maybe. I don't know. I don't know if I'm missing anything, to be honest. Waste proteins. Membrane dynamics. Membrane fluidity. That's in there too. Membrane proteins. Transmembrane proteins. Fluid mosaic model. In there too. What about oh, membrane potential? Which one was this one? Oh, right, missed it. What the heck? Membrane potential. I think this is one of them. Let me check. Yeah, I think so. Maybe all of these, except I don't know if I need to add this one though. I don't want to add it right now. Because I'm not on like Synapse stuff yet. Maybe we can add this. I'm not here yet. Is that what it will do later or no? What is this? Oh, I kind of like these pictures. No. What have you done? There's no way we go over transport across so many. So theory. What?
Oh, there you go. Neuron. Okay, maybe I'll just save memory potentials for that time. Then just remember to have the keyword saved. I'll add in memory potentials after I've done. That's a while. Add memory potentials after week 3. Keyword memory potentials. Week 3. That's on key. That's on key. It's on key. I think that might have been everything. I want to add these, but I just don't want to. I don't want to mess it up. This is all hyperpolarization, which that's actually potentials within neurons, neuronal cells, nerve cells. I haven't done that yet. I want to wait for it. This one I can add though, I think. It's pretty simple. Yeah, I think that's it. That's all I'm going to do. But there was, I just, why do I feel like I'm missing something? No? Am I not? I don't feel like I am. Oh, signal transduction. Signal transduction. There's this one in here. What the heck? Biology. I feel like biology is pretty good, I think. And this one. Maybe we can add this one. I guess. And this one too, sure. Cell junctions. Larger gated channels. Yes, tight junctions. Gap junctions. Desmosomes. What is a desosome? Desmosome. Yeah, we got that. What else am I missing? Actually, I can maybe take it from here too, huh? Plasma membrane. Jingle bells, jingle all the way. Up the wonders to ride in one horse and sleigh. Hey. Jingle bells, jingle all the way. Up the Florida just to ride in one horse open sleigh. What? One horse open sleigh? I think that might be wrong. Oh, primary active transports. Yeah, that's on there. Secondary active transports. It's on there too. Sodium potassium pump.
See, there you go. I guess I can just add this one. Just don't want to go crazy with it.